My name is David Sedlak. I'm the chair of the Water Science and Technology Board and a professor in the Department of Civil and Environmental Engineering at the University of California, Berkeley. On behalf of the Water Science and Technology Board, I'd like to welcome everyone to the spring meeting and on the effect of the energy transition on the nation's water resources. There's a slide supposed to change. There we go. To start, I'd like to acknowledge that this building of the National Academies is physically housed on the traditional land of the Nacotchtank and Piscataway peoples. We honor with gratitude the land itself, the people who've stewarded, and the enduring relationship that exists between these peoples and nations and this land. I'd also like to review our expectations for conduct. The National Academies is committed to fostering a professional, respectful, and inclusive environment where we can all participate in a harassment-free and discrimination-free atmosphere. We look to each and every one of you to help us maintain a professional and cordial environment. For a bit of background, the National Academies is a nonprofit, nonpartisan organization that provides independent, objective advice to inform policy with objective scientific findings. We recruit experts in a variety of fields to participate in advisory work and confronting challenging issues for the benefit of society. Our boards serve as neutral convening bodies that provide guidance on water program priorities, resolve controversies, do technical assessments or independent peer reviews, and increase the visibility of emerging science and policy issues. The Water Science and Technology Board is the focal point of water-related issues at the National Academies. The board focuses on topics such as water quality, quantity and accessibility, ecosystem management, water infrastructure, and hazards. This slide shows the Water Science and Technology Board's current membership, which includes a wide variety of volunteers across many science and water resource topical areas. Yeah, I should mention that we were in a place of transition, and we have 4 new members who will come in at various times during this meeting, participating, and will be part of meetings in the future. Next slide. The Water Science and Technology Board is sponsored by the National Science Foundation, and today's topic that we're focusing on is the effect of the energy transition on water resources. So to paraphrase Yogi Berra for a moment, it's really difficult to make predictions, especially about the future. And when it comes to the future of energy, I think it's pretty clear that we can predict some major changes in the next decades. And so we all hear quite a bit about the energy transition, the nation's aspirations towards decarbonization, but the aspect of how this affects water and how the availability of water will affect or possibly limit the energy transition gets a little less attention. And when it does get attention, it seems to be almost as an afterthought of unintended consequences. And so our intention here of convening this meeting was to try to educate the board and our stakeholders in some of the key issues surrounding this. So what we've done today is we've organized a full day's session, I guess 3 sessions, first starting with the effect of water on energy, and that'll be the first panel. And then the second session, which will look a little bit more at the role of water systems in energy and kind of energy balances at a larger scale. And then a third session thinking about the social and justice aspects of the water energy transition, especially the unintended consequences. So I wanted to say also before we get going that if you want to learn more about our board and board activities, we have a website and you should check that out. We're really happy that you're with us today. And one final note is that people online or even in the room can submit questions for our speakers and panelists on the webpage live stream. Just look for the Slido box underneath the live stream video. And so if you have any questions or problems with that, please get in touch with us or send a chat. But I'd like to, I guess, get things started, kicked off by passing it off to Dr. Nusha Ajami, who's a member of the Water Science and Technology Board, who will be chairing this panel. Nusha.
Thank you, David. It's really a pleasure to be here. I would just say, as a personal note, this has been a topic I've been very interested in, and I'm quite excited we are having this meeting. For the introductory session, I am joined by two of my colleagues and friends, Dr. Peter Glick and Dr. Ashlyn Slewell, and they will discuss the importance of water in the decarbonization pathways. First, we'll have Peter to share a few slides. Peter is a leading scientist, innovator, and communicator on water and climate issues. He co-founded the Pacific Institute in Oakland, California, and developed one of the earliest analysis of the consequences of climate change for water resources. Peter, can I invite you to the lectern to share some slides? Thank you so much.
So I guess I can't control my slides, is that right? Either way. So I'm delighted to be here. Thank you, Nusha. It's great to be at the Water Science and Technology Board and see some old friends and colleagues. I actually served 2 terms on the Water Science and Technology Board. I'm a big fan of the board. One of the challenges of the board is that water is so broad. It addresses so many different aspects of so many different pieces of the challenges that we face. And partly that's reflected by the fact that there is no US Department of Water, but that water is found in almost every aspect of every federal agency. We did a study a few years ago at the Pacific Institute. I think there are more than 20 federal agencies has some role for water. And I think that's probably reflected by some of the participants and observers here today. And I'm going to give sort of an overview. There are 2 focused panels that are coming a little after ours to talk about water and energy and water and where it fits into the decarbonization question. In part, water is relevant for energy. We use a lot of water to produce the energy in this nation, either water withdrawals or water consumption. That's the first part of this graph that shows hydropower obviously is produced with water. Thermoelectric cooling requires a tremendous amount of water. I'll come back to all of this. Fuel production, every aspect of the fuel energy cycle requires water. But similarly, there's a tremendous amount of energy that's required for the water system. And the 2 panels later on are going to go into these in more detail. But energy is required to extract and move water from one place to another. It's required to treat the drinking water that we require. It's required in all of our end uses of water, and I'll talk about each of these, and wastewater treatment at the end. So water and energy are very closely connected, and yet we don't deal with them that way. They're often dealt with institutionally with separate organizations. They're often dealt with from a policy perspective. This is actually a key thing that the Water Science and Technology Board and the agencies that support it can deal with. Is some of the cross-disciplinary challenges here. And this is a graphic that shows the same kind of thing. We take water out of natural systems. That's the thing on the left in the green. We use it for pre-treatment of water, for moving water from one place to another. We use it in the green on the other side, on the right side, for water use. We collect wastewater and treat it to a very high standard. Typically, that's a very water-intensive process, and the cycle goes around and around. On the water supply side, this is a graphic for California that shows the energy requirements for new sources of water. And they have enormously varying energy requirements depending on the source of the water, depending on the location of where you are. The x-axis is the energy intensity in kilowatt hours per acre foot of water. And I apologize for those of you with metrics, but those of us in the West use acre feet, and acre foot is about 1,230 cubic meters of water. When there's not a big bar graph, when there's a small little figure, is a pretty accurate estimate of the energy requirement to produce an acre foot of water. And you can see desalination of seawater is very high on the energy requirement. It's a very energy intensive process. The second one down is the State Water Project. We move water from Northern California to the Central Valley and Southern California. The energy requirement varies depending on where you are along the system. So it could be the farther down the system you are, the more energy is required to move water there. And so that's why there's a big bar graph there. And you can see as you sort of go down, some of the sources of water have relatively low energy requirements. And so understanding the energy consequences of your water policy choices is an important factor, but we typically don't address that. It's sort of addressed in the price of water, but it's not really reflected in the true cost of providing water and the true cost of choosing new sources of water. We also did a study a number of years ago with the California Energy Commission looking at the water-related energy use. And in fact, the energy requirement for water systems in California, and I think this is probably similar elsewhere, are quite substantial. 20% of the state's electricity use goes to the water system. The vast majority of that turns out to go for end uses, primarily heating water in our homes and in water use in industry. Only about 14% of the electricity that's used for water goes to water treatment and water supply. A little sliver goes to wastewater treatment, but a quite substantial fraction of the energy requirements for the water system go to end use, which is an important policy question we can talk about later. About a third of the state's non-energy natural gas use goes to water. This is not the natural gas that's used for power plant generation, but all of the other natural gas that's used in California, about a third of it goes to the water system. And again, the vast majority of that turns out to be primarily heating water in your homes. If you have natural gas heating, that's where a lot of it goes. But it's a substantial fraction. And this is understanding these connections between water and energy are important from a policy perspective. We've also done a lot of work at the Pacific Institute about alternative sources of water, alternative supplies, the role of water conservation and efficiency. This is a graph that simply shows the cost of a whole range of water options in California, from conservation and efficiency, landscape changes, replacing toilets and washing machines, all the way to desalination. And it's an estimate of the relative costs. I guess is there no laser pointer here, but the ones on the bottom that are blue have a positive cost. The ones that are on the top that have green actually have a negative cost. And what that means is it's more cost effective. It pays you to do those things. You make more money over the long run, the life cycle, if you've implemented in particular water conservation and efficiency, as opposed to building desalination or finding new groundwater sources or new traditional reservoirs. Those are not cost effective. And I'm showing this only because the most important point here is these things that are really cost effective are largely cost effective if you look at the energy savings involved in them. Because you're not just saving water, which saves you some money, but often you're saving energy, which often means you're saving a lot of money because energy is relatively expensive. So for example, when you replace a toilet or a washing machine or a dishwasher, especially things that use hot water, you're saving a lot of energy. But even when you replace a toilet, you're saving the energy required to treat and move that water to the end user. And if you don't include energy in those calculations, the cost numbers are different, and you don't get a proper estimate of the value of doing these different options. So that's another reason why including energy is critical. There's some emerging trends in the water and energy field. We have growing populations. We have declining urban per capita water use because of conservation and efficiency. We're shifting, again, in California, but also elsewhere, to more local sources. That's in energy savings. If you don't have to move water long distances and you use more local sources of water, there's an energy savings there. We're seeing greater electrification of end uses. I'll talk about that a little more in a second. And decarbonization of the electricity grid. All of those play a role in economics. They play a role in greenhouse gas emissions. That's the climate, water, energy nexus. And the combined effects of these trends is not really well understood. This is a graph of a study we did a couple of years ago, just actually recently at the Institute, looking at the role of urban water efficiency in California for meeting water, energy, and climate goals. And we looked at 3 scenarios. The middle scenario is if in the future, per capita water use in urban areas in California stays about the same, the amount of water used per person. That's the middle 3 graphs. And if that's the case, you have an increase in projected water demand because population's growing. Per capita water use is the same, but population's going. So projected water demand goes up. Water-related natural gas use goes up. Water-related electricity use goes up. And greenhouse gas emissions go down. And that's sort of an odd conclusion. But the reason for that is because we're decarbonizing the grid over time. So electricity use goes up, but more and more of California's electricity over time, over the period of time of these scenarios, which I think was till 2030, I'll have to go back and look, is from non-carbon energy sources. But if you go to the far right, you have declining per capita. If the assumption is we're seeing declining per capita water use because of improvements in water conservation and efficiency, which is actually what's happening in California, you can see a decline in water demand, even though population goes up, a decline in natural gas use, a decline in electricity use, and a very substantial decline in greenhouse gas emissions associated with the water system, again, largely driven by this decarbonization. And that gets to one of the questions you've asked here about the role of energy and water and decarbonization. It's really critical to decarbonize the grid, because that's feeding into a lot of the demand for energy for the water system. We did a series of urban and agricultural case studies as part of this. Just a couple of quick examples. The Los Angeles Department of Water and Power is shifting to local sources. They're trying to move away from reliance on the long distance transfer of water in California, which is energy intensive, it's politically divisive, it's economically costly. So they're shifting more to imported water. From imported water to local sources. That's an energy savings and a greenhouse gas emissions savings. The Colorado River, of course, is overextended. They're trying to reduce reliance on the Colorado. So that's an example. The East Bay Municipal Utilities District, which is actually my utility up in Northern California, has an energy recovery system at their wastewater treatment plant. Turns out there's a lot of energy in wastewater. And they have a system to recover energy in their wastewater system. And they're actually now producing more energy from their wastewater recovery system than it costs to treat the wastewater. Again, another water energy connection. And California also has something called the Sustainable Groundwater Management Act, finally to try and regulate groundwater. Groundwater pumping in the Central Valley of California is very energy intensive. It's overdrafted and groundwater levels are dropping, which increases the energy cost of pumping groundwater, an economic cost to farmers. If we can restore and replenish groundwater, groundwater levels can recover, reduces the energy cost of groundwater, another connection between water use, policy, energy, and so on. And more of those groundwater pumps in the Central Valley are not diesel, which is a greenhouse gas problem, but electricity. On the other side of this, that is water for energy. This is a classic example. There's a lot going on here, but basically this is the water, the consumptive water requirements to produce a kilowatt hour of electricity from a whole range of energy sources. And the only thing to note here is that there's a lot of variability. Different energy sources require different amounts of water that's consumed. There's also a separate graph for water withdrawals that's a little bit different. But the bottom line here is that some of the renewables, most of the renewables, are very low water using. Takes a lot less water or no water to produce a kilowatt hour of solar or wind compared to producing a kilowatt hour of coal-fired or thermal or any number of traditional energy sources. And again, we did a study for the Intermountain West, a series of scenarios looking at the water requirements, both water consumption and water withdrawal, for different scenarios. The far left is 2010. That was the current data in terms of water requirements in million gallons per day for the Intermountain West. And the bottom line here is that shifting from once through cooling systems to recycled cooling systems reduces the amount of water required for those energy systems. But shifting to renewable energy from traditional thermal, nuclear, and fossil fuel really reduces the amount of water required. So again, energy for water, water for energy, the two panels this afternoon will go into more detail. But our decisions at the national level or the local level about our energy choices also has an enormous impact on our water requirements, which in turn has political consequences, ecosystem consequences, because you can leave more water in ecosystems if it's not required for energy production, and many other advantages. And I think other speakers will talk about that. So key takeaways: water and energy are interconnected in a lot of different ways. There are a lot of challenges to dealing with those interconnections, but there are a lot of opportunities for saving money, for saving political capital, for reducing greenhouse gas emissions. Water policies and regional and national energy policies both are key to meeting water, energy, and climate goals together, but we don't typically integrate across those institutions. Energy savings makes water efficiency measures more effective, and water efficiency measures are already some of the cheapest, fastest, most environmentally smart things that we can do, especially in water-constrained areas around the world. And energy savings from water efficiency are cost competitive compared to other energy efficiency programs. It turns out some of the cheapest ways to save energy now are not energy efficiency programs, but they're water efficiency programs. It's cheaper to invest in a water efficiency project. You get more energy savings per dollar than investing in some of the energy efficiency policies that we've traditionally invested in. Urban water efficiency offers great reductions in water-related energy uses and greenhouse gas emissions. But in particular, we want to replace imported water with local water sources. That's an important factor in reducing greenhouse gas emissions. But we also want to decarbonize the grid. The faster we can decarbonize the grid, the faster we can take carbon out of all of those energy requirements. That, coupled with greater electrification of end uses, so if you're heating your home water not with natural gas but with electricity, that's an important decarbonization factor as well. Energy efficiency and electrification with renewables offers opportunities to reduce energy-related water use, and that creates a virtuous cycle with a lot of characteristics. And I'll stop there. Thank you very much.
Thank you, Peter. And next, we have Dr. Ashlyn Stilwell. Ashlyn, yeah, go ahead, please. No, go ahead. Ashlyn is an associate professor at in civil and environmental engineering at the University of Illinois, Urbana-Champaign. Her research focuses on creating sustainable water and energy systems in a policy-relevant context. Go ahead, please.
Great, thank you. Thanks for the invitation to be here. And I'm really excited to follow Peter in his excellent setup for this whole day and give you some more perspective on some of the work that we've been doing on water and energy as it relates to this context of decarbonization. I actually want to start by acknowledging my students that do a lot of this work. It's not really possible to do university research without excellent graduate students. And so I want to start there. That way, in case I run out of time, I don't forget to thank them. So a lot of the water for electricity work that I'll mention is being done by one of my current PhD students, Jenny Nugent. And the energy for water work is something that we've done a few years ago with my former PhD student, Dr. Chris Cheney, who's now at PNNL, Pacific Northwest National Lab. And that's a link to the two main publications that I'll talk through today. So in terms of thinking about decarbonization, water and energy are both really important context for decarbonization. Instead of thinking about the grid in isolation, it's important to consider both water and energy. And my student Jenny made this particular figure, and I think it helps illustrate kind of some of the context that matters here. A lot of times in the energy sector, we are generating electricity at a discrete point in space and time, and then moving that electricity to end consumers. And as we have more people living in urban areas, it kind of feels like we've gotten increasingly stretched in where the impacts are happening and where the consumption is taking place. And so what that translates to is water consumption and water withdrawal for power generation at one location, with kind of the burden of that electricity consumption then shifting to another place in space and time. And that comes from both hydropower and from thermoelectric power, and then that use of electricity and other energy sources in different sectors of the economy, with the water sector being an important consideration. And so kind of starting with this perspective of water for electricity, we asked ourselves, how does water for energy vary on the US electricity grid? And this picture is from NERC, and it is a general smattering of the North American electricity grid. This is Canada and the contiguous United States. And these polygons here are balancing authorities. These are subsectors of the grid itself where we are balancing supplies and demands on a smaller geographic scale. And those are connected to each other, but also within the broader context in large interconnections. And there are loose connections between those. So for example, ERCOT in Texas is only loosely connected to the rest of the US electricity grid. So just a picture to keep in mind in terms of how water is virtually moving on the electricity grid. And the reason we care about this is because electricity demand and water availability and the fuel resources that we use to generate electricity vary seasonally. And a lot of times we only focus on annual versions of these particular data. And that can paint a different picture if we're only looking at annual numbers versus seasonal numbers. Some things like nuclear in the bright green line are fairly constant throughout the year. And that's very different from natural gas, which is the dashed purple line at the top that very much peaks in the summertime in response to increases in electricity demand. As Peter mentioned, the grid itself is changing. Demands on the grid are also changing. As we electrify everything, we are likely to have not just a summer peak, but also a winter peak in places that currently depend on natural gas for heating. If we were to electrify all of that, we are likely facing a summer peak and a winter peak in terms of electricity consumption. And so that has implications for what kinds of fuels we use to generate that electricity. And because generating electricity requires water, that means we're consuming water in different places and different times throughout the year. And so what we did in our analysis, we know how to do math, but I don't like to put equations on slides, and so I put pictures instead. We take the monthly water footprint, in this case, that's water consumption of a particular balancing authority, a subset of the grid, divide it by the monthly generation of that balancing authority, and then multiply it by the interchange of electricity between different balancing authorities. And so when electricity is generated in my home state of Illinois from a nuclear power plant, that water is consumed, but the electricity might end up being used in Minnesota, for example, depending on when and where those demands occur. And so with that information, we start to consider how the water consumption on the grid changes both spatially and temporally. Each one of these dots represents a balancing authority. It's just the centroid of that balancing authority. A warmer color dot is a larger percent export. And so that means they're virtually exporting water by exporting electricity. And the thickness of the lines represents the amount of water consumption that is associated with that electricity transfer. And it's kind of mesmerizing to watch how this changes over time. And there's different areas that pop up as particularly important. You see a large link between what looks like Iowa and West Virginia, but that is MISO and PJM, kind of big aspects of the grid itself. But there's also some interesting things happening in Arizona and California, particularly in electricity that is generated using water from the Colorado River Basin that is consumed and then exported to other consumers of electricity. As Peter mentioned, there are other ecosystem implications that come along with water requirements for power generation. And the way that we capture that is with a concept called gray water. And this is the same sort of figure for gray water. Gray water in water footprint literature is a bit of a weird concept that I don't necessarily agree with. It is the amount of water that is needed to dilute pollution. In the case of a thermal power plant, however, we are literally diluting pollution, which is waste heat. And that amount of water that is needed to dilute that waste heat is represented in this factor of gray water. And really, this gray water transfer figure is capturing the strong dependence of power plants in the Midwest and the Eastern interconnection that continue to rely on open loop cooling or once-through cooling. There's a significant amount of water withdrawal, much smaller water consumption, but if that water is not there in the first place, those power generators are not producing. And we see that that varies in time, both in the summer and another peak in the winter time as well. And so having data to back these decisions up is really important. And so if we go back to that question of how does water for energy vary on the US electricity grid, what we see is that there is a significant variability both spatially and temporally. As we build more transmission lines, have different electricity demands in time and space, we are virtually moving a lot of water resources around on the grid. Those blue water transfers, that traditional water consumption, are really prominent in the Midwest and the Southwest, but gray water, the impacts on aquatic ecosystems, are prominent in the Eastern United States because of once-through cooling. Another thing I want to point out as I transition to energy for water is that there's significant uncertainty in these numbers. We're using as much reported data as possible, and you can see the shaded region around the line. There's a lot of uncertainty in the data that are reported and in the physical basis of those data. And so kind of pivoting to the other side of the rest of the day today, we asked ourselves, how does energy for water vary across the United States? And really, we wanted to put numbers to this value. And so similar sort of idea in terms of data, we collected data. We collected those data from water and wastewater utilities through open records requests. If you've never submitted an open records request, it is not a way to make friends at all, but it's a way to fill in data where you have no data. And a lot of water and wastewater utilities in the United States are public utilities, which means that's the best way to get data from them. I could speak at length about what it was like to try and get data from water and wastewater utilities, and open records requests were an interesting adventure. With those data that we collected, we took the energy consumed divided by the water or wastewater flow treated to get a metric of the operational direct embedded energy in kilowatt hours per cubic meter for water and wastewater systems. And so when we visualize those data, this is what we got. This is based on a 9-month data collection effort for drinking water utilities across the United States. We did our best to get a representative sample across all 50 states and DC. The size of each one of those circles corresponds to daily per capita drinking water consumption, and the color of the circle corresponds to the embedded energy, where the warmer colors have higher energy associated with them than the cooler colors. There are some that don't have a color associated with them that are white. That's because they either didn't have energy data that they reported, or their data didn't make a whole lot of sense. And Kansas City is a good example of that. I grew up near Kansas City. The Kansas City water system is wonderful because it's Kansas City, but it's not all that interesting, to be honest. And it's a traditional surface water treatment system. And the data that we got from Kansas City on energy, when we divided that by the flow that they treated, were 2 orders of magnitude higher than all of the other data that we had here. And so my student Chris went back to his contact and he said, hey, I think something might be up with the data that you sent me, or they might be in the wrong units. And they said, nope, that's what we got. And so we considered that maybe an error and didn't report those data. But big takeaway here is that if it looks like there aren't any trends, you're absolutely correct. We ran tons of spatial statistics. There are no significant trends associated with location in determining how much energy is required for drinking water treatment. We did the same on the wastewater side of things. Similar thing here, size of the circle is per capita wastewater generation. The color of the circle corresponds to embedded energy. Really, the only trends that we see here are associated with the presence of combined sewers, which makes sense. As we have cities with combined sewers, they should have more wastewater generation per capita than separated sewers. But again, very few no statistically significant trends when it came to energy embedded in that wastewater volume. So when we requested these numbers, we asked how much flow do you treat and how much energy does that require? And we got some interesting results in the numbers that came back. These are 6 representative cities that reported monthly data. And the solid line corresponds to drinking water volume. These are just drinking water numbers. And the dashed line corresponds to the embedded energy in kilowatt hours per 1,000 cubic meters. So drinking water has a summer peak associated with it. Most of that corresponds to residential irrigation. And that's something we kind of expected going into this data collection effort. We also expected that embedded energy would follow a similar temporal trend like we see in Dallas and Oklahoma City on the two in the bottom row, left and center. We figured that would be pretty typical because we're moving more water through the same diameter pipes. They should be losing more energy to friction. It should follow a similar trend. The 4 other cities reported here actually have an opposite trend. And this is a function of how we requested these data. We asked for how much energy does it take to treat water, or how much energy does it take to provide that treated flow of water. These utilities reported all of their energy, not just electricity. They reported electricity consumption, but also the primary fuels that are required to heat the buildings and to operate the entire system. And so what we see there is the presence of natural gas in keeping buildings heated in the wintertime. They're not heating the water, they're heating the buildings in order to operate treatment operations. And this is something we didn't anticipate going into it. Most of the time in the literature, we're focused on electricity. We're focused on the electricity to run the pumps and the electricity for the treatment process itself, not necessarily the primary sources of energy in the form of natural gas. We also asked the utilities how much their non-revenue water is. This is leaks or any water that's not paid for in an accurate manner. There are some spatial trends here. Really, it corresponds to the age of the infrastructure. Older infrastructure is leakier infrastructure. And in some of these cities, we're looking at 45% non-revenue water, which is quite high. That is almost half of the water that's treated at the treatment plant that does not make it to a customer that is accurately paid for. And so when we put all of this together, we really learned a lot from this process, that energy for water and wastewater includes both primary and secondary energy sources, secondary as electricity that's gone through a conversion, and that varies spatially and temporally. There's no centralized database that reports these values, and so when you don't have numbers to make decisions from, it's really difficult to manage and benchmark that resource. We also extrapolated from the energy associated with drinking water and the non-revenue water values that we got, and found that non-revenue water is about the same amount of energy as 300,000 US homes. So it's not just focusing on end use efficiencies, it's also fixing all of our leaks in our leaky distribution systems. And so in a 1-slide takeaway, I love that we use the same clip art, and that tells you how important these things are. Water and energy really are an important context when it comes to decarbonization. It's not just transitioning the electricity grid, it's also considering the water associated with things. So I think with that, we turn it back to Nusha on a panel discussion. And if you've got questions that don't get answered today, this is how to find me. So thank you.
Thank you, Aisling. That was such a great discussion. I really appreciate you both putting these slides together and providing such important context for this day. I'm just wondering, how are we, can we see the panel? Yeah, we have a view of the panel. It's working.
It's working. There we are.
It's coming. It's coming. Okay, perfect. There we go. Okay. I have a lot of questions, but I'm going to start from one thing that I think you both mentioned. I think maybe I would like for both of you to reflect on that, which is, what are the sort of implications of lacking the system level perspective when you're talking about the water and energy or decarbonization? You sort of touched on how we generate energy and have water footprint in one location, and then the electrons are used in another location. We also, I think, Peter, you touched on how, for example, when you look at location, energy footprint, solar panels and wind turbines might, or wind generation might look really low in water needs, but the reality is somebody somewhere made these panels and made this turbine. So the question is like, what are the sort of impacts in another location while you're not accounting for it? So I would love to hear your perspective on that. Either one of you want to start?
Again, lend some perspective on the energy side in particular. And I think that's an interesting contrast among different locations. One of the things that we see in data over time is that widespread and prolonged drought very much shifts how we generate electricity. And this happened in California in the very long drought that really compromised the hydropower generation system. And how do you make that up? Well, natural gas was primarily the source that filled in gaps there. I think part of what is going to be really interesting in the future is how climate change affects different locations that historically haven't known how to cope with that. And I'll take my home state of Illinois as an example. We don't know how to argue over water quite like California does, because we've always had enough to go around. And so that implication of drought in Illinois could affect electricity prices in New York City is something that I don't know that we necessarily think through. And as we change the electricity grid and we change those demands, I think there's some important considerations around price and around the impacts associated with that. Do you want to add?
Yeah. So there were two parts to that question, but the key problem of not evaluating these resources, analyzing these resources in combinations, you make the wrong decisions. The incentive to invest in water conservation and efficiency in the Western US is already very high. It's already the cheapest source, new source, if you will, or demand reduction of any alternative in the Western United States. But it's far more cost effective if you include the energy savings. If you don't include the energy savings, you're underestimating the economic benefit both to utilities and to end users. And typically we have not included those costs. So water utilities will give you a little bit of a rebate for a water conservation device because they don't see the energy savings directly. The consumer might, but the energy savings that the utility gets isn't typically reflected in that. Now, there's some exceptions to that. So for a number of years ago, my wife and I bought a high efficiency washing machine. Saves water, saves energy, saves detergent. We got a rebate from the water utility and a rebate from our electric utility. So sometimes the policies interact. You can get combinations, but if you don't include energy and water, you don't always make the right choices. And similarly, obviously the incentive for renewable energy now, because the price of renewables has dropped so dramatically, is great. But that price doesn't reflect the water savings and the ecosystem benefits of not having to take water out of ecosystems or additionally overdraft rivers or aquifers. Dr. Stillwell mentioned this, but I'll reiterate it. there's this difference between water consumption and water withdrawals, and we've talked a little bit about both. And some people think, well, the only thing that's important is consumption because that's water lost to a system. But the reality is, even in, for example, the Southeast, power plants have had to be derated or shut down during droughts in the Southeast, nuclear power plants and coal-fired power plants, because there wasn't enough water in the system during a drought for the water withdrawals required for power plant cooling. That's an energy cost. And again, we don't think about that in our energy and water policies.
Just also to provide some context for everybody. So we are going to have this panel discussion, and then I'll open it up to everybody else to ask questions. So just hold tight. It's going to be another 10 minutes, and then I'll come to you. So Peter, on that, actually, I want to go back to these policy discussions because I think it's really important to think about disconnect between different states and the policies that are in place, right? One state might not have as stringent policies around water extraction. I mean, we sort of taught that in what you were presenting, water extractions, or actually even, I don't know, we did a study a few years ago looking at, fracking in New Mexico that ends up becoming clean electron in California, right? And they don't have any regulations around fracking, right? So then the community there potentially could have been impacted from water perspective. But we in California, we ban fracking, so we can't really sort of, right? But I mean, the reality is we are not counting that as a clean electron, right? So I think, what do you both think these disconnect between policies from state to state, community to community, can impact this system level perspective, or the fact that we need to do better in managing these two resources?
Yeah, so I have mixed feelings about that. I mean, obviously, to some degree, the extent to which we can normalize and integrate policies across state lines or across utility borders or across balancing systems would be helpful. But sometimes individual state policies can help drive some of that. So California, for example, a long time ago now, implemented some of the first water efficiency standards, very strongly opposed by the appliance manufacturing industry, but for toilets, washing machines, dishwashers, shower heads, that kind of thing. And then Massachusetts adopted them, and then a couple of other states adopted them. And then the industry said, we don't want 50 different states. We don't want to make appliances for 50 different state standards. And they ultimately supported what became the federal standards for those things. And so sometimes state standards and policies are important. Sometimes federal standards are important. And one other quick comment on this. Another disconnect, for example, is California has a policy now on carbon credits that provides quite substantial economic resources for certain kinds of energy policies. But those carbon credits those financial benefits are not available to the water sector at the moment. A water utility that says, look, I can reduce greenhouse gas emissions by, for example, like installing a wastewater treatment system that recovers energy and reduces greenhouse gas emissions. They're not eligible at the moment under state policies for decarbonization. It's a disconnect. And when I said earlier in my talk, just quickly, that some of the cheapest energy efficiency policies and decarbonization policies are water policies, that's not reflected by some of these state strategies.
Yeah, I think it's a multi-pronged policy approach, quite honestly. I was reflecting on the last time I spent a lot of time in Washington, D.C., and it was coming up on 15 years ago that I interned at the Congressional Research Service, and I was working on a report for a couple of senators who wanted to know how would the presence of renewable energy generation affect water resources. And so this is not a new conversation. We've been talking about this for a very long time, but that's the pace at which things move a lot of times in policy. Is it takes having the conversation and accepting an incremental change, recognizing that we are indeed moving forward, even if we're moving forward very, very slowly and compromising along the way. I think there also is an important role of state-based policies, and especially around things like energy. We've seen that in Illinois around things like the Clean Energy Jobs Act that recognizes it's not just the utilities, but also a workforce issue. As we talk about end uses in particular and the residential sector, that is many, many homes that would need to be retrofit. And the truth is we don't have a robust workforce that is ready to install heat pumps in every single residence in the United States. There's a need for recognizing the whole system. And I think that's a good role for policy to play, is to look at the whole system and see where gaps exist and where we might be able to fill some of those gaps synergistically.
Maybe a follow on to that, and Peter, going back to the comment you made on sort of the carbon market that we have in California. How do you think, first of all, why do you think that gap exists, right? We have these silos, right? We do water and then we do energy and we do carbon. I actually literally think there's another silo for carbon, which is not necessarily, sort of touches on energy, but not all the time. How do you sort of break these silos, and what are the different strategies that, and I think this goes to the context of financing as well, because we're talking about money flowing into each sector and trying to enable investment across different sectors. What do you think are what do you think is missing?
Well, the first answer is you gave in your question, which is we're siloed institutionally. That is the problem. And honestly, I mean, I'm a scientist. I don't know the best way to overcome some of those things, except you educate the policymakers. So when they set up the policies, they think more broadly. They think not just energy, but water when they think about carbon markets. When you set up the carbon market system or whatever system you're setting up, and it's hard to break those silos. You know, we don't have a Department of Energy, a Department of Water at the national level. We have 20 plus federal agencies. There's the USGS, and you know them all. And there is an interagency water group at OSTP that does some work in this area, but you all know how rare it is for there really to be truly interagency. Bob should probably address this better than anyone. It's hard to break those institutional barriers, and I don't have a great answer for that, for how to do that, but that's something we need to do. Okay, so the Water Science and Technology Board should propose a committee at the Academy about breaking the water, energy, climate silos.
And I think on that topic, you also, I also wonder, these silos also causes the way that money, I mean, manages the way that money moves, or sort of limits the way that money moves, right? So that kind of like also impacts, you can have policies. I think it's not just a policymaker thing, because policymakers can think broadly, as you said, 15 years ago, talking about, and I'm sure, you know, you can go even further back and see people talking about it, but then it comes down to implementation, and that's where sometimes you have issues with turf, maybe.
Yeah, let me add one comment about that, because that's a really good point. And I touched on it, and I think Dr. Stilwell touched on it a little bit. So I talked about the multiple economic benefits by doing this kind of integration, but those economic benefits don't always accrue to the right agency or the right end user. I mentioned that the economic benefits to the end user of certain policies might make sense logically, but if the money goes to electric utility or a water agency, the money you have to figure out how not just to cross the institutional barriers, but the financial barriers.
I'll just add one thing, because you ended your question with what's missing. And one of the things that I think is great about the lineup today is there's a discussion around social implications. And when we talk about money and we're talking about water and energy, there's a large amount of the population that already can't afford their water bills and already can't afford their energy bills. And so recognizing that we have very important resources, people who can't afford them, yet these resources are necessary for life, is one consideration. And as we're talking about money, the energy sector and the water sector have very different amounts of financial resources associated with them. I think we all kind of have that sense, but in terms of overhauling a system, most water utilities are not flush with cash to do that. And so that's why we have 45% non-revenue water in some places, because there's challenges around rehabilitating that infrastructure. It'll be interesting to see how some of these new PFAS regulations get rolled out and how that affects how systems are operated, how treatment is operated, and what that looks like on a consumer's bill.
Oh, yes. Okay, I do recognize it's 11:55, 8:55 in California. So I want to open it up to the audience and allow them to ask questions. One thing that Charles reminded me, please make sure you include your questions in the Slido. We have colleagues that are following that closely, so we can share your questions. This is for people who are on the, online. And then also for people here who want to ask questions, please use your mic, because we want to make sure people who are online can hear you. And with that, David has been waiting patiently.
Yeah, so I'm David Sedlak, Chair of the Board. First, I wanted to thank you both for your remarks and also for coming in person. It's so wonderful to see you here and not just on the Zoom. And that doesn't reflect on any of the people who stayed home and couldn't make it today. I appreciated what Ashlyn said about the slow pace of change, but we heard from Peter about decarbonization in California and how sometimes change happens very quickly. I saw Peter give a talk about a week ago where he was about as positive as I've ever seen him about seawater desalination. And I think it comes back to the last point in his talk about how once we decarbonize the grid, some things become possible that 20 years ago we would have been very concerned about because of the greenhouse gas implications. So I want to challenge both of you a little bit to think about maybe the grid of 2050 and assume that decarbonization happens faster than you might imagine at a national level, maybe becomes something like the way it's happening in California, and think about what it means for the blue and the gray water. Ashlyn and Peter, think about and maybe tell us a little about what it means for intensification of water treatment processes as an alternative to new water resources when conservation can't get us where we want to go.
To your blue and gray water question, I appreciate that. Thank you, David. I think an important aspect of that ideal grid of 2050 is around the nuclear question. Is it a renewable grid or is it a low carbon grid? And we've had to make that distinction in our policies in the state of Illinois because we have such a large presence of nuclear power generation. That's not to say that nuclear is perfect, and nuclear is subject to a lot of water constraints, and we've seen that play out. But I think that's an important question as we think about, do we put a Band-Aid on the current nuclear sector? Do we do widespread rollout of small modular nuclear reactors? What does that mean for water? But having some perspective on this ideal grid of 2050 that is decarbonized, how that translates to water impacts, I think nuclear is the big swing. If we embrace nuclear, then we have a lot more base load, but a lot more water dependence. And France is an interesting example there of having that strong dependence through one particular fuel source can leave you quite vulnerable to heat waves. And that can translate to widespread problems if we're moving more electricity from one place to another because of build out of transmission.
And what about, where would hydrogen fit in there? Like,
Good question. I'm smiling because a number of conversations with BP have made hydrogen a very interesting one. And the context, I think, is really important in how we do that accounting. In some respects, water consumption on its own is not a bad thing. It just really matters on context. Are we consuming water in a place that has plenty of water in a sustainable manner? And just because it rains a lot in a location doesn't mean that we're using our water resources sustainably. I think that consideration has to come into play. If we are generating hydrogen in an area that is already water stressed, then perhaps that's not the savior we thought it was.
But David, I'm going to have to go back and see what I actually said about desalination. And I've never been opposed to desalination. I always think about it in the context of alternatives. At the moment in the United States, it's the most expensive alternative. It's far more expensive than still untapped water conservation and efficiency. It's even more expensive than pretty expensive high quality wastewater treatment, collection, reuse. And so we've always argued at the Institute, if you include all of the costs of these different options, do the things that are cheaper and more environmentally beneficial first. And desalination just doesn't rank in that case at the moment. And that was partly reflected by the cost figures I showed and the energy cost of desalination. And it doesn't matter if the energy is nuclear or fossil fuel or solar. What matters is the cost of the energy. When you include carbon and the possible cost of carbon, that adds a cost if we're properly paying for the price of carbon emissions, which of course we're not really doing at the moment. But it gets to the other part of your question, which is decarbonization. So suppose in the imaginary future we're decarbonized, and I think we will be eventually, then that takes that out of the cost equation. It takes it's still, you still have to evaluate the other economic costs of the environmental challenges of desalination, which is proper brine disposal. There are other environmental coastal impacts, that kind of thing. But if you can decarbonize, then you take carbon out of the cost challenge, and you still have to deal with the other questions about what's economically appropriate and socially and politically and culturally.
Can I add one more thing?
Yeah.
I just wanted to address kind of an underlying assumption there. We haven't electrified everything yet. And in that grid of 2050, if we have indeed electrified everything or have found a sustainable replacement for applications that very much depend on liquid fuels like transoceanic aviation, for example, I think that also changes the temporal demands and the spatial demands on the grid. If we've electrified the entire chemical sector, for example, that changes what the picture looks like.
It's a great topic for dinner conversation, I think. Thank you, David. Okay, I have an audience question, and then I can go to you, Venkat. So we have a question that has came through. The next frontiers are outside of California in places without a wide recognition of scarcity and drought, growing cities in the Southeast. What has California learned from their transition? What would they do differently with the time machine?
Well, there are a lot of similarities between what California is facing and other water-stressed regions, but there are a lot of, there are institutional and legal differences. I mean, I'm not sure exactly where that question wanted me to go, but one thing I would do differently is I wouldn't develop the water rights situation in the West the way we have it today. And if I could wave a magic wand, I would change the water rights regime because it greatly complicates water policy. It sort of removes economics from a lot of the picture. It's incredibly politically intense, but I can't wave a magic wand. Having said that, if you had asked me that question a few years ago, I would have said, well, gee, it would be really nice if in the Western US we had groundwater law. And now we do. Again, circumstances change. And so there are policy, I guess my point is there are policy opportunities to do things differently. And broadly outside of California, I would argue for the same things I've been arguing here, which is integrate across these institutions, integrate water, climate, energy, agriculture from a policy and an institutional perspective. And the decisions you make are more likely to be productive and effective.
Okay, I have Venkat and then Crystal. Please also introduce yourself.
Venkat Lakshmi, member of the Water Science and Technology Board, professor at the University of Virginia. Thank you so very much, Peter and Ashlyn. What fascinating thing, and again, having been on the edges of it and not in the middle of this discussion and conversation like you guys, I am probably very ignorant about many of the details. So when I think about this problem and think about it as a multivariate optimization problem with some economic numbers, which actually I have no idea about, other than reading The Economist a couple of times a week. I don't have any idea. Is there an attempt to solve this coupled water energy problem at different scales? You know, I know Ashlyn showed a wonderful pictorial of how the water was going blue and the gray water. Wonderful, fascinating. Is there a way to frame and solve this problem at different scales? You know, one could be a very, very small catchment based optimization, and one could be global when you said trans-Pacific airplane transport, you know, and all that stuff. Is there a way to do that, or is there a way at least people have started thinking about it? Thank you very much.
Well, you know, different policies apply at different scales, and there are different institutions that are able to work at different scales. David mentioned I gave a sort of optimistic talk a few weeks ago. It's because I have a book that talks about the past, present, and future of water, and I'm optimistic about the future. And part of the reason is there are a lot of success stories already happening at a lot of different scales, where Singapore, for example, is collecting and treating and reusing basically 100% of its wastewater, including producing incredibly high quality wastewater, so high quality they're using it in their semiconductor industry, which requires ultra pure water. California treats and reuses about 18% of its wastewater now and has plans to double that. There are, and I gave a couple of local examples of, you know, Ebmud's wastewater plant is producing more energy by collecting and treating the wastewater and collecting the energy associated with that than it costs to treat the wastewater. Those things can be scaled up. Some of them are very local and small scale, and some of them are require larger interventions. So it's a great question, but it depends on the problem and the scale and the region.
Yeah, similar thoughts that context really matters. And it could be that the single home is the appropriate scale for that. And it could be that deeper system integration is a better example and a better way forward, where having thousands of distributed things is not as efficient as having 100 distributed things of a medium size. And as you mentioned, East Bay Mud, I thought of my own wastewater utility that takes waste from the Kraft plant down the road in Champaign and waste from mac and cheese manufacturing, high organic load, which means high biogas production if they combine those two systems, municipal wastewater treatment and a high organic loading. That's an example of a synergy where having two separate entities closer tied to each other would be a good thing. But then in other instances, where you make things really closely coupled and then you have some sort of disruption, that cascades. So I think context is a really important consideration there.
I think that was a great example. And I would also quickly say on this whole synergies, they also can provide some financial mechanisms that enables these some of these activities to actually thrive and survive rather than constantly struggle with lack of finances. Crystal, please.
Crystal Tully Cordova, Water Science and Technology Board Member, Principal Hydrologist for the Navajo Nation. So I'm curious, you know, we've gone from Navajo Nation having Navajo Generating Station, coal burning power plant, and that being decommissioned, contributing to water in the region. So that used 35,000 acre feet of water. And now, you know, our projects, water projects on the Navajo Nation are relying upon crisp water, which has great vulnerability because of the drought conditions in the region. And so I'm kind of curious about other energy sources that you may have recommendations for. Right now, there has been discussions about hydrogen development in the region, as well as a lot of hydro pump storage projects. And, you know, for a place, I realized, you know, Peter, you did have a description about, you know, more local water sources to be able to decrease that energy. But when you have alluvial aquifers that are very vulnerable to drought, at the same time, you have a population, a third of its people don't have running water. And I'm just curious about the energy sources associated. I mean, we went from decarbonizing our uses to be able to rely on hydropower, but at the same time to see, you know, Ashlyn and Peter, if there's recommendations for other energy sources that can benefit, I mean, not just tribal communities, but rural communities, because when you look at WAPA and all of those who are reliant upon hydropower and are very vulnerable, yes, there's efforts to be able to manage Lake Powell and Lake Mead in a synergistic way. But when you have policy like the law of the river that challenges the upper and lower basin and the need for energy, but also the need for water, how do you address that? Or what are some energy source recommendations for being able to continue to decarbonize, but then that may not, I mean, when you think about a lot of the energy, a lot of them are reliant upon water. So I'm just curious if you have recommendations or thoughts for places for rural America that have this nexus that's so tightly knitted. Thank you.
One resource that's two resources that are especially useful are wind and solar. And because those don't require cooling, they don't have direct water consumption implications. And that's something that we've really seen that has transformed certainly the Midwest, the rural Midwest, in the distributed scale of solar, distributed scale of wind has really changed some of the economics in very rural areas. My parents grew up in a very rural part of Northeast Missouri, and the main source of income in the county is Social Security, so quite economically depressed, but a lot of land and a lot of wind potential. And so that has really kind of transformed the ability for a lot of family farmers to make ends meet. And it's kind of funny to drive through and see solar panels on a rickety old barn, and the solar panels are worth more than the barn holding it up. But it is this distributed in space energy generation, which does lead to more resiliency, and it decouples that dependence on water.
Yeah, I would just add a couple of points. One is, I'm not sure I'm qualified to answer the question for the Navajo Nation, but I agree with the wind and solar, almost zero water requirements, very low water requirements. But I would couple it with battery storage because, of course, the storage issue is increasingly a factor with renewables in terms of load management. And your point about the Colorado River is a relevant one. The Colorado River is oversubscribed. We're having enormous political battles for which the Native American communities are barely even a voice about sharing the Colorado River and the energy requirements from Lake Powell, for example. And so finding ways of meeting both the water needs and the energy needs in the region is an ongoing fight.
Thank you both. So I just want to mention that we have microphones in case you need to have a question or you want to ask a question of our speakers. You're ready to ask a question? Yes, go ahead, please. And could you please introduce yourself as well?
Hi, everybody. I'm Josh Weinberg from the Alliance for Global Water Adaptation. I will try not to speak so long before questions, but we'll get to the question directly. But I think there's sort of two sides that we're looking at with this discussion. One is about emissions reductions from water via energy, and then the other side is about vulnerabilities and resilience of the energy system through water management. So for this, I maybe ask the question directly, maybe on that side. Like, what do you see as the key vulnerabilities that need to be addressed, and what would be useful for the energy sector utilities to address some of those vulnerabilities? An additional comment is also, as you started to mention a little bit with storage, I think this is a huge factor also when we look at sort of the water requirements of the energy transition. Now we're having some studies where they're wanting to factor that in when we look at wind and solar power, for example, if you're going to need water from pump storage, hydro, or for batteries, and what maybe if those are going to have some implicit vulnerabilities to them that need to be addressed.
Well, maybe the greatest vulnerability that's not been addressed is climate change. Obviously, our energy system is dependent on water in a lot of ways, and hydropower directly on water. And again, Dr. Stillwell mentioned this during droughts in the Western US, hydropower generation, for example, in California, drops from an average of maybe 18% of the electricity system to 8 or less of the electricity system. And often we have to make that up at the moment with natural gas, and there's a greenhouse gas. So it's climate change affecting water availability, and loss of water availability increasing greenhouse gas emissions. It's sort of this negative feedback loop, or positive bad feedback loop, if you will. So extreme events is a critical issue on the water side, and related to that on the energy side. And our water systems and our energy systems are not yet adequately integrating climate into longer term issues around resilience. That's another one of these synergies.
I'll just add infrastructure. Each one of these sectors has a need for significant infrastructure investment, either in expansion and access for individuals who don't have access to water, or insufficient transmission lines to move electricity generated in remote areas to places where it is demanded. And that takes investment. In upgrading infrastructure for the energy sector or the water sector, that takes investment. And how we do that in a sustainable manner that can respond to those extreme events is really important. Also recognizing those equity implications, because when that investment is just passed on to a consumer and they see their bills double, that raises a whole bunch of social implications.
And maybe infrastructure is also where we can take advantage of synergies, which we don't often right now, right? Sort of like.
Yeah, that's a good point. Just to reemphasize that, the point that Dr. Stillwell made about non-revenue water, that's water that utilities treat. They spend the energy and the money to collect and treat and distribute it, and they don't get revenue from it. And there's an energy cost there. So the ability to invest in infrastructure to reduce non-revenue water losses has multiple benefits. There is a lot more money now in the new infrastructure bill. It was $80 billion in one form or another for water-related investments in the infrastructure bill, including $15 billion for lead pipe replacements. So there is some money for infrastructure now, but again, as Dr. Ajami mentioned, there's a lack of adequate financial resources for utilities to address some of these issues.
Thank you. I'm going to go to Pedro, and maybe I use my moderating power, and there's another audience question which I would like to ask. And I look at Deb and Charles and say, maybe we go a little bit even longer. Thank you. Pedro.
Oh, here we go. Thanks for the great talks. Really nice. I'm Pedro Alvarez from the board. And I just had a question. If you could make a call to action to DOE, or, where to request one thing. Imagine you being emperor or empress for one day, focusing on DOE. What would that be?
I would love to see the residential sector fully electrified in a resilient manner. And that's harder than it sounds in areas that depend heavily on natural gas for heating, and in areas that are not adequately insulated. The low-income weatherization assistance program gets us part of the way, but we still have a lot of homes that are these distributed consumers of fossil fuels. To the extent we can electrify the residential sector, that's what I would do.
I would add there's an enormous lack of data for some of these things. It would be great if DOE or other agencies could expand their analysis, for example, of the water requirements of energy systems, or the energy requirements of water systems. Again, we saw a great variety of first of all, a lack of data was mentioned, but then a spread in the actual data. Because when we have those data, then the policies to address decarbonization or reducing energy requirements for water systems, or water requirements for energy systems, becomes clearer. And so there are all sorts of research projects that cross the traditional DOE boundaries that need to be pursued.
And maybe also that data would help us to benchmark these utilities and agencies against each other. So kind of like,
Yeah, one quick comment about that. From first principles, we sort of know pretty clearly how much energy is required for different wastewater treatment processes. We know how much energy is required for ultraviolet purification or filtration or disinfection from wastewater treatment plants. So we do know, even though the utilities, the wastewater utilities or the water utilities reported a wide range. You know, Dr. Stillwell pointed out that part of the data problem was they're reporting all of their energy for heating buildings and not just the treatment. So there are different ways of getting to the data question. We're just not very systematic about it.
okay, last question from the audience, actually. The question goes to PFAS and other sort of contaminants that needs to be treated. How would the question is, can you please speak about how new contaminants specific regulations will affect water treatment and water reuse policies in heavily contaminated sites?
It's going to increase the energy consumption. Meeting stricter quality standards is something that will increase energy consumption for treatment. And my understanding of PFAS is quite limited. So I'm looking at David, he's smiling. So maybe he knows more. But my understanding of PFAS is that the best ways to treat it are all energy intense. We're talking membranes and other expensive ways like granular activated carbon. And then how do you regenerate that? It's called a forever chemical for a reason. So we've got some work to do.
So I have a little different perspective on this, and maybe it's sort of a generic response. The wastewater, the water treatment systems in the United States are often old. We built them 100 years ago or 50 years ago. A lot of them need to be upgraded. There's a lot of new technology that can produce incredibly pure, high quality water. I don't know, again, maybe David or other people in the room know the extent to which these more modern systems will not just deal with PFAS, but with a whole range of other chemicals that we're already worried about, but we may not have standards for. And if we can upgrade, broadly speaking, the water treatment systems in the United States to 21st century standards, we could probably treat a whole range of chemical contaminants that aren't being treated adequately right now. Now, there's a huge economic cost to doing that. I'm not minimizing that. That needs to be done anyway. And part of the challenge is finding the money to do that. But maybe if we brought, you know, again, maybe the desalination, the membrane, ultraviolet purification, the combination of treatment systems can deal with a lot of these new unregulated or recently regulated contaminants. And we have to figure out how to pay for it and how not to burden the communities that are already challenged with high costs of water. And David wants to respond.
Really quick.
Go ahead.
I'd like to just build on what Peter said, and I think it's not just the drinking water treatment plants, but wastewater is still a big source of PFAS contamination, and it kind of pushes us towards treating the wastewater and recycling it. So potable water reuse programs remove PFAS, and it kind of gives us a chance to build that next generation water system in places where water scarcity is also a driver.
So that's a great example where you get two bangs for the buck. You want to collect and treat and reuse wastewater. And if by doing so, you're using the advanced purification systems, you solve that problem as well. Yeah, thanks.
And maybe also moral of the story here is maybe we should also prevent some of these chemicals ends up in our systems. Then we need to clean them up, right? And then maybe we need to go back and look at the Toxic Substance Control Act and see maybe some of these things need to be eliminated. So with that very, very positive note, I'm going to close this panel. Thank you both. That was a very lively and thoughtful discussion. I appreciate that. And please join me to thank Peter and Ashlyn. And
We're not thanking David.
no, we're not. He's sitting right in front of me, so it's very hard. So I want to thank you for that, for joining me. And just a quick thing. So I think we're going to break till 1. You know, this is lunchtime here. So for those who are online, please join back around 1 o'clock. And then we're going to have a discussion about various decarbonization pathways and what are the potential water footprints of that. So for now, we'll pause for about 40 minutes. Thank you, everyone.
Thanks for coming back and joining us. So my name is Kirk Ellison. I work for the Electric Power Research Institute and our Water and Land Research Group, manage that group. So glad to be with you all today to moderate this session. So we're going to go ahead and get started for sake of time, so we have time for plenty of questions. So our first speaker is Andreas Clarence. He's a professor at the Department of Civil and Environmental Engineering at the University of Virginia, and he's also the Assistant Director for Industrial Decarbonization at the White House's Office of Science and Technology Policy. His research is focused broadly on understanding anthropogenic carbon flows and the ways that CO2 is manipulated, reused, and sequestered in engineered systems. So Andreas, come up and join us. Thank you.
It's good to see a bunch of familiar faces. I'm Andres Clarence, and I want to start off by thanking Charles for the invitation to share a little bit about what the Biden-Harris administration is doing to help enable the energy transition in the U.S. and think more broadly about what the transition will do, how it will intersect with water resources. As Kurt mentioned, I'm the Assistant Director for Industrial Decarbonization in OSTP, the Office of Science Technology Policy, in the Industrial Innovation Team, which is focused on applying scientific and technical expertise to implement the President's Investing in America agenda. So the team works across various emerging technologies, including clean energy, biomanufacturing, semiconductors. Most of our team is focused on President Biden's net zero emissions by 2050 goal. Achieving this goal will require unprecedented mobilization of resources, as well as creativity and the need for a lot of creativity and innovation. And so that's why the president, along with Congress, have matched that ambition with investment. You all may be familiar with the Inflation Reduction Act, the Bipartisan Infrastructure Law, the CHIPS Science Act. These laws represent the largest investment in climate and clean energy that the world has ever seen. This will transform the U.S. and global energy system, and collectively it'll amount to building a modern American industrial strategy, and that is what our team is focused on. And so this is a government-enabled, private sector-led initiative that will view the private sector as a partner, not a rival, and invest in every stage of commercialization to get new clean energy solutions and other strategic innovations developed and deployed at scale. And so thanks to Bill, CHIPS, and IRA, we've seen an incredible amount of growth in clean energy and clean transportation deployment. And so coming, from a university context where many of you all are, to work in the White House 2.5 months ago, it's really been breathtaking to see the scale of what this administration has accomplished and what's happening out in the world. So in 2023, we added more utility scale solar to the grid than ever before in history. And in 2024, we expect to nearly double last year's record. The grid battery storage industry was nearly non-existent in the U.S. Before President Biden took office. Since then, we've seen a tenfold increase in deployment, and that's just accelerating. Electric vehicle sales have more than quadrupled since the start of the administration, beating forecasters' expectations by 18 years. And so the energy transition is very much accelerating. And on the surface, the major trends that we're tracking here are good news for water resources. Making an electron from wind or solar has, over a life cycle, much lower water footprint than making electricity from coal or natural gas. The EIA is tracking those data. You can find them on the EIA website, and you can see very clear decreases in the need for water for power production. But it's also important to acknowledge that the most recent national climate assessment, which President Biden announced this past November, says that climate change will continue to cause profound changes in the water cycle, increasing the risk of flooding, drought, and degraded water supplies for both people and ecosystems. And so it's important to know that that's a big part of the reason why the energy transition must accelerate. And so, moving forward, the water and energy production will continue to be linked in important ways, but in increasingly new ways. And I applaud the Water Science Technology Board for beginning the important work of anticipating those intersections. And as we advance the clean energy system, we need to use every tool to cut our emissions, and we need to make sure that we're using those tools safely and responsibly. And so I was asked to come and speak today about the role of carbon capture and storage and how that fits into the energy transition broadly and where the intersection with water resources might exist. So I'll start by saying that carbon capture and storage is a key enabling technology. For many years was seen as a critical tool for decarbonizing the power sector. CCS is the process of capturing CO2 from usually from point sources and injecting it into the subsurface, deep geologic repositories where it can remain trapped, usually through some kind of impermeable cap rock or geologic formation above the target repository that prevents buoyant flow from having that CO2 migrate to the surface. The impact on water resource, this can impact water resources in a number of ways. During injection, the target formation often needs to be pumped to relieve overpressurization, which can bring brines to the surface, which wouldn't normally be there. Those have to be managed largely through deep well injection in other locations. Over time, a second impact on water resources can occur if injected CO2 migrates out of the target formation and ultimately winds up in freshwater formations, where the CO2 can impact the usability of that groundwater resource by altering the chemistry of the subsurface. These are important processes to understand. From speaking as an academic, these have been studied for a number of years. The news or the talk of the town this week in Washington, of course, and the important implications it has for CCS is the big news from EPA last Thursday, which some of you may have read about in the news. But last Thursday, the EPA released their final suite of standards to reduce pollution from fossil fuel powered plants. I'll mention them all. There are 4 key pillars to these standards, and I'll mention them all because they all have implications for water resources, although only one of them is relevant to CCS. So the first is a final rule for existing coal-fired and natural gas-powered plants. 90% of their carbon pollution must be captured using best available control technology. And so this is, in the language of the EPA, this means carbon capture and storage. So basically what the new rule is saying is that power plants that want to remain active beyond a certain date will need to use carbon capture and storage. And so that's a major scale up if this is the path that ends up that the power utilities end up taking to increase utilization of CCS. And there are all kinds of incentives that already exist for CCS in the suite of legislation that I talked about at the beginning of my remarks. But the new EPA rule is sort of the stick to pair with the carrot of the tax incentives. The 3 other parts or pillars of the new EPA rule are mercury and toxic standards for coal-fired power plants, tightening the emission standard for toxic metals by 67%, which, I don't need to tell this community why limiting mercury pollution is important. The third is reducing pollutants discharged through wastewater from coal-fired power plants. And the third is safe management of coal ash that's placed in areas where that were unregulated at a federal level until now. And so managing the solid residues that come from coal power production. So those 4 pieces amount to the backbone of this really important piece of standards that the EPA released. The best system of emissions reduction for these long-running coal units is going to be CCS, and so the final rule includes requirements to help ensure meaningful engagement. There's a lot of work in the White House on sort of understanding what CCS is going to look like in the communities that are going to host these facilities, and so there's a lot of effort focused on meaningful engagement with affected stakeholders, including communities with environmental justice concerns that have been historically overburdened by pollution and climate change, as well as energy communities and workers who have powered our nation for generations. And so these standards will also require states to provide transparent data and compliance pathways and timelines through the state planning process to ensure that workers and communities have the best available information to plan for changes in the sector. As I mentioned, the bipartisan infrastructure law also provides billions of dollars to advance and deploy CCS through tax credits and build the infrastructure necessary for it. So this is pipeline technology that's necessary for coupling sources and sinks. So finding where we need to inject the CO2 and how do we get it there. And so In light of this quickly shifting regulatory landscape, the U.S. government expects to see much more CCS deployment taking place over the coming years, and that the emissions reductions it will provide will save the country billions in avoided costs. So moving beyond the power sector, I want to highlight two other corners of the energy transition where CCS could be important. The first is the area that I'm most heavily involved in the White House, and that's industrial decarbonization. So heavy industry accounts for about a quarter of all U.S. greenhouse gas emissions, and these have traditionally been thought of as the hard-to-abate sectors of the economy. So hard to abate because it's a very fragmented part of the economy. It's very heterogeneous. There's a lot of different processes involved. Some corners of the industrial space, such as cement, there's significant direct emissions coming from the actual chemical process that is inherent to the industry. About 5 or 6 weeks ago, the Department of Energy Office of Clean Energy Demonstrations announced $6 billion in federal support, unlocking $14 billion in private capital in these hard-to-abate sectors. Two of these projects are carbon capture projects where CO2 from clinker production facilities will be captured and injected into geologic repositories. One's in California, one's in Indiana. And so both are existing facilities. And one of the things about the Indiana facility that's interesting is it's located directly above an injection site. So it's able to inject directly below the factory where they're producing this clinker. And so these projects are going to really start the process of helping to decarbonize the industrial sector. The second sector that's not power related directly, but that has important implications for CCS that I want to point out or highlight here is carbon dioxide removal. So to meet net zero goals, most modeling scenarios suggest that we're going to need to deploy carbon dioxide removal at scale over the coming decades. And this can come in a variety of different forms. So it can come as direct air capture, it can come as bioenergy with carbon capture, come as land-based techniques like spreading silicates on agricultural lands. So there's a variety of different ways in which we can, there's marine CDR, there's a variety of different ways in which we can get this carbon removal. But many of the technologies that are receiving the most attention have as an enabling technology carbon capture and storage. So if you're talking about direct air capture, you can capture the CO2, but if you don't have a CCS plan, something to do to get rid of the CO2 once you've removed it from the air, then your project is not going to be super successful. So each one of these technologies, that cross the carbon dioxide removal landscape will have distinct impacts on water resources. These can be anticipated, but they haven't been particularly well studied yet, just because the market for carbon removal is still fairly small. So globally, the voluntary carbon market's about a $2 billion market worldwide. And, to remove the levels of carbon that many of the integrated models suggest we're going to need to remove, we're going to need to scale that sector by many times. And so anticipating what the consequences of that sector could be for water resources is a really important conversation to have. Especially for direct air capture and bioenergy with carbon capture, because both of those rely on CCS. And I want to point out or highlight or flag BECCS in particular here, because bioenergy with carbon capture, which some people in this room have done a ton of work on understanding what the impacts of bioenergy crops are on water resources, and this is just one of those topics that won't go away. It's been with us for maybe 2 decades, and it continues to persist. If you talk about most forms of BECCS, if you talk about sustainable aviation fuel, which is a really big topic right now, if you talk about a number of areas, the water resource implications of those activities are really important to understand. And so even though the market for CDR is relatively small on a global scale today, the need for this removal is expected to grow. And so understanding how we can do that carbon removal without putting unnecessary pressure on our water resources is just is an important objective. The Department of Energy, Office of Fossil Energy and Carbon Management, around some of these issues that are place-based and really tied to community concerns, tied to water resources, is going to be making a number of announcements over the coming weeks and months about tools that are going to be available for tracking some of these things. So I encourage you all to keep an eye out for that. And with that, I'll just thank the conveners again and grateful that the National Academies is having this conversation. Thanks so much for inviting me.
Thank you, Andreas, for that to get us started this afternoon. So with that, we're going to move to a virtual presenter. So with that, we're going to move. So Dr. Yushan Yan is going to join us. He's the chair in chemical and biomolecular engineering at the University of Delaware. He's the founding director of the Center for Clean Hydrogen, which was launched in 2022. And he's there to accelerate the transition to clean energy, for reducing the cost of hydrogen and hydrogen-related technologies. So with that, take it away. Thank you.
Thank you. I think I need permission to share the screen. Looks like.
You have permission now. Go ahead.
Yeah. Are you all seeing the right screen? Are you seeing the right screen?
Yes.
Okay, thank you. First of all, honored to be here. My apologies not being able to make it to DC, although I'm fairly close. I'm teaching two classes. One is for a graduate student class designed to be very intensive, 5 hours a week FaceTime. And the other one is a undergraduate design class. I'm alternating like 3 hours a week, and then the next week is free. So it's hard for me to leave. Sorry, couldn't be there. And the second is I structured my presentation assuming I'll be here mostly for learning. I think my assumption turned out to be quite correct. And I see the scales presented by Peter Ashland are very large. And then Andreas took it to an even larger scale, adding national policies. So what I'm going to do is take you back a bit to the sort of nerdy technology presentation. But before I do that, I just want to show this standard slides every time I talk. I am the founder and CEO of Versogen, a small startup company of 40 plus people, spin out of the University of Delaware. And so some of the data I'm presenting are from Versogen. I'll be so labeled. I thought I really benefited from the two presentations in the previous session. So I want to show you my lessons from the two presentations. So wind, solar have the smallest water, therefore energy and carbon footprint, making me even more excited about green hydrogen. So thank you, Peter. And from Ashland's presentation, I began to feel every electron moving down the translation line. Next time I raise my hand to see ahead to see the line, it carries and water molecules, many water molecules with it. So I think it's a huge, a piece of knowledge I didn't have. And spatial and temporal consideration are very important in terms of managing our water resources. This is the one you're going to see in the last slides in my presentation as well. Now, I thought it would be helpful for those who haven't done work in the hydrogen space. So I want to just tell you the colors of hydrogen. The first one is green hydrogen. Maybe I can get my pointer working. So green hydrogen, by the way, the difference are in the water source, the material source, and the process itself, and the energy source. So for green hydrogen, the hydrogen source is coming from water, and it goes through electrolysis, meaning using electricity to split water into hydrogen and oxygen. And the energy source is solar and wind. So this is a green hydrogen. The hydrogen we're trying to replace is this gray hydrogen. You start with methane and go through steam methane reforming, and you use heat as the energy source. So this is the one occupies 95+% of our hydrogen supply today. And relevant to this conversation, if we use nuclear, and that is called pink hydrogen. So now I see green hydrogen is advantageous over pink hydrogen from the water resource perspective. And I won't go into other categories. One question I've been asked quite regularly is green hydrogen necessary for decarbonization? Green hydrogen, in our view, is an able, necessary partner for green electrons. Green electrons will do what they can, will do a lot, but there are certain places they're just not, capable of doing the decarbonization. And hydrogen especially has strengths in industrial feedstock, and that is majority of the applications today, roughly 100 million ton per year worldwide. And the application, I think, represents the best example for green hydrogen is the ammonia synthesis. So we use the Haber-Bosch process, and we take nitrogen from air, we take hydrogen from natural gas, and we make ammonia. So this is making a linkage to food security. And the hydrogen from natural gas has a very large carbon dioxide footprint. More than 10 tons of carbon dioxide is produced per ton of hydrogen. So if we are able to replace this hydrogen with green hydrogen, we'll be reducing carbon footprint quite dramatically. So in our opinion, hydrogen is necessary. So it's no longer a question whether hydrogen will be needed. It's really a question of how much we will need it. The particular green hydrogen technology we've been working on for the past close to 20 years is this hydroxide exchange membrane electrolyzer. And I want to talk about this technology in the context of the two much older technologies out there. About 100 years ago, we have this liquid alkaline electrolyzer. So you use potassium hydroxide as the electrolyte in the middle to separate the two electrodes. So one electrode is producing oxygen and the other electrode is producing hydrogen. And this one is very inexpensive because the catalyst is inexpensive. The bipolar plate connecting the cells are inexpensive. About half a century ago, proton conducting membrane came into existence. And this one is in an acidic environment. This one has high performance, meaning you can pull a lot of current density, and that means you can produce hydrogen at a much faster rate. But the downside, the other benefit of this one is it has this dynamic response capability, so you can follow wind and solar. And another benefit is a pressurized hydrogen, so you can do the first stage pressurization this is very beneficial because most of the applications for hydrogen at the end requires some pressurization. So the device we've been working on in the past 20 years is this hydroxide exchange membrane electrolyzer. So it is in an alkaline environment. So that is why hydroxide is going through the electrolyte. And it also has this membrane approach. So it has the ability to deliver all the good things the previous two technologies could. We are using very expensive catalyst, very inexpensive bipolar plates. We could have high performance. We could have dynamic response. We can deliver pressurized hydrogen. So if you look at the approach my research group has been taking in the past 20 years, more than 20 years then, is really from proton conductor to hydroxide conductor, or from acid to base. We actually do carbon capture using similar technology. But if you look at what we need for this hydroxide exchange membrane electrolyzer, we need a new membrane. The proton conductors using Nafion, this is the proton conductor that has been there for half a century, very durable, very high performing polymer. I have heard PFAS in the previous conversations, so there is a concern about that for that particular polymer. But in order to move to hydroxide exchange membrane, we really needed a new polymer. And this is what we came up after many years of research. And I won't bore you with the organic chemistry. So this polymer has very high ionic conductivity and is very stable in alkaline environment and mechanically very robust. And was good enough for me to be convinced to found Versogen. This is a startup company. We started with 0 employee quite a few years ago. If you look at the scaling we've been doing is quite significant. We started in lab for less than 10 gram a batch, and today we can do much more than 15 gram a batch using a much larger reactor. So this is the scaling factor we have been able to achieve. And then in peripheral membrane scale up, we started with drop casting, just a liquid drop on a petri dish or glass plate, so you can produce membranes. And now we produce the membranes row to row, so we can produce hundreds or thousands square meters per trip if we want to. And if you look at the hydroxide exchange membrane, we already have this one as a commercial product. We have a capacity of 1 gigawatt per year, and we have many customers around the globe. We have a steady growing revenue. But our dream was bigger than the membrane. We wanted to make electrolyzer stacks. So this is the central piece where you put water in, electricity in, you actually produce hydrogen. So this is really the core component of a hydrogen plant. And we have very ambitious goals of reaching 1 megawatt unit by the end of this year. And this is the standard size used by most of the stack makers out there. And the other effort I want to introduce to you is a Center for Clean Hydrogen I started a few years ago. This is a partnership of University of Delaware and Chemours. Chemours is on the University of Delaware campus, is the world leader in making Nafion ion exchange membranes. So this is the proton conductor one. And then Plug Power, I would say Plug Power is the American green hydrogen company. And then the National Renewable Energy Laboratory, NREL is a leading lab, or perhaps the leading lab within the DOE national lab system for green hydrogen electrolysis. The thesis of this center was 3 years ago, talking to Comoros. We anticipated a lot of companies are going to come into this hydrogen space, but most of them are component companies, like making a membrane or a catalyst or a bipolar plate. And so they would need a testing capability to do the testing for them so that they can make informed decisions. And these decisions could be many $1 million, could be hundreds of $1 million. And having a center like this is very time consuming, very expensive. And they wouldn't be able to justify doing investment themselves. So we figured if we were able to convince the federal government to support a center like this, and everybody will benefit, they can move to the market faster. And of course, this is a university-based center, so we want to do research and education, and I want to do entrepreneurship. But once we have this massive scale testing capability, we will be able to provide some uniqueness to the research we do, to the education we provide, and to the entrepreneurship we advocate. So that's basically the idea. And then last year, we were very fortunate to be awarded one of the 7 hydrogen hubs in the Mid-Atlantic region. This is including Delaware and South New Jersey and Southeast Pennsylvania. And as a UD faculty member, I'm leading the higher ed workforce development for the whole hub. And I just want to make a bold claim, since I'm a faculty out of the University of Delaware. I believe we have a very historic opportunity and perhaps an unparalleled ecosystem in Delaware for green hydrogen. I want to start with saying, my research group is doing one type of electrolysis, and Versogen as a company is scaling that technology. And we have a center that will serve all the component companies for their scaling effort. And we have this Mark II, hub for technology deployment. So this is your first market. And with companies like Comoros and Gore and Versogen, I think Delaware is an undisputed capital of ion chain membranes. And with the hub, with companies like Bloom Energy on the UD campus and Air Liquide a couple of miles away from UD campus, we will become a capital of clean hydrogen. Now, this is where I want to show the consideration we made for the water resources. We are not expert in this area, so this was our limited attempt to answer this question, because I get asked, does green hydrogen have a water problem? I'm very proud of this paper because this was done by an undergraduate student of mine, Rebecca, wonderful student. She later became a National Science Foundation Fellow and Goldwater scholar pursuing her PhD. So we did a lot of reading of the literature, and this is the global water consumption and withdrawal for the expert out there in water. I'm sure this is very basic. So the message I want to deliver here is, even in the most optimistic estimate of the future green hydrogen economy, the amount of water we consume is still relatively smaller than the agricultural use, and also smaller than the fossil energy production, power production system. And the idea is at some point of time, because of the advances we make, these systems will shrink. So maybe it will free up some water for us. So our conclusion was, at a global scale, it doesn't seem we have a water problem, but it could be at a local scale or at certain times. So this is really the spatial and temporal consideration for the water problem. I think I'm going to flip to one page for my acknowledgement, and I'm stopping now, and happy to answer any questions with my fellow panelists.
Well, thank you, Yushan, and we will hold questions till we're done with our third talk. So our third
Okay,
talk is
sorry.
Oh, no, great. We'll do it all together as a group. So our third talk here is going to be from Dr. Brendan Moran. He's a postdoctoral research fellow at the University of Massachusetts Amherst. He's going to be joining us virtually. He's from the Department of Earth, Geographic, and Climate Sciences and part of the lithium solutions research team there. And Brendan has been working to understand the many complexities of natural water cycles where lithium and other critical mineral resources occur. So looking forward to the talk. Thank you.
Hi, everyone. Can you hear me first of all, I guess? Does that work?
Yes.
Okay, great. I will go ahead and share my screen here. Presenter mode. Can you see just the slides?
Yeah.
Awesome. Awesome. Yeah. So thank you very much. Once again, thank you for all the conveners. It's really an honor to be here. And yeah, like the other, panelists, I would have liked to be there in person, but I wasn't able to. So I have a lot of detail here, but I'm going to try to work through that and really just hit on the main points. And I'd like to have time for discussion. So yeah, so hang on one second here. Yeah. So yeah, I'd like to really speak about our work here, trying to really reframe water issues when it comes to lithium mining. I think there's really a need to reframe issues when it comes to water with lithium. So quickly, here is the global map of lithium resources. Western Australia has a lot of hard rock lithium resources. In the Western US, we also have a significant amount of resources, which will obviously become, even more important in the near future with Biden's initiatives and really reshoring and trying to get a national resource going. Right now, there's only one operating mine, Thacker Pass, right there. Labeled is a new resource, a clay resource that's going to be really important going forward. But I want to focus on one of the hot spots really in the world, which is we call the lithium triangle in South America here. And these are closed basin continental brines, and really they're the most important global resource. They are now. They will be going forward. A lot of about half of the production now is hard rock, but these brines are really, really important. And there's several in the US that are going to be explored in the near future as well. One of the important points about these brines too is that they are the least energy and water intensive of all of the resources. So that's another key sort of reason why we think these are going to be the most important. Another sort of aspect of lithium resources really across the world is that they happen to occur in arid water stress environments. And so water is limited, and it becomes even more critical when it comes to lithium because of that. So here's just a quick schematic of a continental closed basin brine system where the mining of a lot of the global lithium occurs currently. We have fresh water, we have brackish water, which is really the interaction with the brackish with the fresh water and the brine, which is the resource, the lithium resource. So the mine, I'm gonna get this laser pointer out here. The actual mining of lithium occurs on the basin floors in these brine aquifers. So there's really a range of distinct water categories, water characteristics, and within these systems, and the interconnections between these water categories is really, really important. And oftentimes it's been sort of overlooked or lumped together, but it really has to be split out. And so the resources in the environment are really inextricably linked. And so water footprints, which is a common way of looking at water issues, is really too blunt of an instrument. It's really just water use. So all water use really is the water footprint. And here we really need to split out what water we're talking about. So it should really be reframed to incorporate the relationship of water with the environment and to humans. So contextualizing these sort of water types. So fresh water can be broken down into sort of water quality categories. So what it can be used for. And then further, when we're talking about these really arid, large basin, closed basin systems, we have a whole other distribution of water that includes sort of industrial water, they call it, so sort of above the livestock watering category, but not quite this brackish or brine water. And we get these brines, which are very, very salty water, 5 to 8 times saltier than seawater. And some work we did in 2022, looking at the largest currently operating lithium mine in the world, Salar de Atacama in Chile. We looked at the water budget of the basin and incorporating a lot of new science in terms of actually breaking down the water budget into a much higher resolution. And so we showed that the natural waters, so really all the water that exists in the system, it covers a wide spectrum of physical characteristics. Salinity can be one; it can be broken down that way. But there's also the source of the waters and the transport times and the age. So this, especially in arid places like this, the water tends to have a large distribution in age, and it can actually cover up to millions of years. In this case, we think a lot of these waters are hundreds of thousands of years old. And it's really important to also break it down into those categories. So obviously, fresh water is the most critical to humans, and it also happens to be most critical to sustaining natural systems. Even though a lot of the sort of wetlands here are actually brackish water, they're saline wetlands. The freshwater input we've shown is actually has an outsized role in sustaining those. So sort of a takeaway is we really need a more nuanced understanding when we're talking about water budgets, when we're talking about impact attribution or water allocation. We really need to understand the natural system a bit better than we do at the moment. And I think some of our work has pushed that forward in the last 4 or 5 years. Yeah, that was a little lag there. So we did some numerical modeling work. This is some work from my colleague Dan Corcoran, which is in review at Science Now, and we looked at the difference between really extraction of freshwater aquifers versus the extraction from brine aquifers, and the responses in the system are quite different. Really more different than we expected. One key note of that is you can see these springs here. These vectors here are spring discharge, so fresh water discharging near the basin floors, and really important to sustaining wetlands. You can see from 1-to-1 extraction of fresh water versus brine, you actually lose the springs entirely, whereas with the same amount of brine extraction, you don't lose those. And so the takeaway is that freshwater extraction also is more important in terms of a 1-to-1 than brine. And so we really need to, understand, when we're talking about total water use, we can't really lump these two together because the impacts are not really comparable. And so, yeah, freshwater use is really, really important. yeah, and yeah, I'm gonna move on. So yeah, so freshwater is really uniquely sensitive to impacts from its use in these environments, and it really needs to be, at the forefront of water impact discussions. So we did some more work looking at so water availability, the availability of water resources in the lithium triangle. So this is that region of South America where a lot of the brine resource exists. We recalculated the available water, so the water that's available to ecosystems and to humans for use. Freshwater, this is freshwater, and we subtracted demand, which is really human demand in this case, and also environmental requirements for environmental flow requirements. And we got to a availability versus demand. And one thing to note is just how low the amount of water is in these regions compared to the global average of 160. These are all in the tens, single digits of available water. And we knew that, but our recalculation really showed that there's even less water available than we originally thought, than most studies have shown. And so it becomes really important to sort of manage this fresh water and make sure we're not overusing it. And so, yeah, fresh water, the availability of fresh water really needs careful considerations in terms of where it's being used and how much it's being used, how much is, sustainably able to be used. And this has potential consequences for avoiding sort of unintended consequences when we're talking about, this direct lithium extraction is a new technology that promises to reduce brine use. But a lot of times it actually needs more energy inputs or more freshwater inputs. And we don't want to cause, more problems by using more freshwater to reduce brine. In this case, we would probably recommend not using more freshwater at all. I think that's, but it depends on where you're talking about. Yeah. So some summary thoughts. I think really we need to reframe how we think about water when it comes to mining. I think mining in terms of lithium in particular, but also that this comes into play with copper mining, with any large scale mining in an arid area. I know the copper demand has skyrocketed, and there's going to be a lot more extraction of copper. These same issues are there, and so yeah, we really need to have hydrological context when we're talking about water issues, water use, water impacts. And so, yeah, just quickly, some sort of science research priorities we can do to push to improve our understanding of this sort of water, this hydrological context we pointed out. We can improve evaporation and recharge estimates in arid areas. There's currently a lot of uncertainty about how much actual water gets into the ground and also how much is leaving. Those should be improved. And also these interactions between the brine, the salty water, and the fresh water there's still a lot to learn about where these interactions occur and how they affect how they're affected by use. And also sort of water budget pictures, large scale water budget assessments really don't incorporate longer timescales in them currently. So water that takes a long time to get to the basin floor or to get to the freshwater resource really is missing from a lot of water budget assessments. And I think it should be really incorporated into those. Yeah, and I just want to do a quick plug for Leanne Monk, my colleague and really mentor, who will be speaking at another board in a couple of weeks. About like more detail about these science questions. So I invite everyone to check that out. Thank you.
Thank you.
All right, so with that, we're going to move along to our question and answer part of the panel. So I will start off with a question or two, and then certainly move around and take questions from the board, as well as those of you online who are dropping questions into the chat or through Slido. So Andreas, since you're in the room with me, I'll start with you. So thinking about carbon capture, I know with the power industry, and we get a lot of questions from those folks who have power utilities, and good questions starting to come up saying, okay, we have the technology of carbon capture, but what about all of the parts and pieces on the kind of timeline of getting this siting and permitted at our site? So we're getting questions around, well, we can start to define the additional water use that might come with post-combustion capture, but what does that mean if I say have a natural gas plant that's sited on a small waterway and it looks like I'm going to double my consumptive water use? So what does that start to do to me from the standpoint of my water intake permits, my water discharge permits, that sort of things? And I think the question comes in is around timelines there. And, am I going to be able to, is the timeline of all my siting and permitting, which is often state-based, going to align with standards that I own on the other side? So any thoughts you have on kind of all of those ancillary water parts on the carbon capture?
Yeah, it's a really good point and a really good question. Thanks. Yeah, it's a really good question. So for a long time, the bottleneck was really the Class 6 wells and the permitting around those, which are the EPA well classes that allow you to do deep well injection of CO2. My understanding is that permitting process has gotten resourced and is much faster now. So that is no longer the bottleneck. I believe that more of the bottleneck right now, from a federal perspective, really is around the transmission and the pipeline development and issues there. But PHMSA's release, I don't know if they've actually released, but they're working hard on new rulemaking to accelerate that process as well. So yeah, there are a number of different layers in terms of permitting that need to be addressed in order to allow the industry to sort of implement this, right? But the administration's working hard to try and do that. As far as the state perspective, I don't know that I'm the right guy to answer that, but I think that you're right in the sense that a lot of times that those end up being pretty significant impediments.
Great, thank you. And yeah, it's a good conversation. We can perhaps continue more later this afternoon. So with that, just for fairness, I'll kind of move around for questions, and Yushan, I'll ask a question for you. So just Brendan, get ready. I'm moving down the line. So Yushan, so I was curious of your studies around water use for hydrogen and some of your conclusions. I was wondering kind of some of the assumptions that you've made in some of those studies around the water use for cooling around hydrogen production for electrolytic hydrogen. I know that's a big question. There's a big bar around the water use for hydrogen production when you start to think about, are we going to use dry cooling systems, wet cooling systems? Are we going to go with a industrial scale model for electrolytic hydrogen or a more distributed model? So I'm curious any additional thoughts you have around the water picture around hydrogen.
Yeah, this is a great question. The study we had, I just showed to you, that one was really just considering the water consumption for producing hydrogen. And the cooling part wasn't considered. So clearly, when we do water electrolysis, the process is not 100% efficient. And so there's quite a bit of electricity will go to generating heat, and that has to be managed. I don't know the number, but clearly that need to be considered.
Thank you. And did you also, in your water numbers, did you just use the stoichiometric water numbers, or are you also considering like the water losses of the water treatment to make the high purity water?
Yeah, just I think we considered, there's a deeper analysis in there. When we did the reverse osmosis, like desalination, we did consider, you're going to double roughly the amount of water you need. But overall, that bar was really for fresh water.
Great, thank you.
Yeah.
All right, so Brendan, quickly moving on, so the board has time for some questions here. So just a quick question, any thoughts from your work on brine management once it's at the surface from those really high specific conductance brines?
Yeah, that's a great question. Yeah, that comes up a lot. Yeah, so it's important, sort of the way that a lot of these mines operate is that they actually mine on the evaporite surface, so on the salar, where it's essentially the native material is the tailings. There's no, there's no additions made generally. So, in those cases, it's just a cycle. They pile it up, it dissolves and goes back into the aquifer. When we're talking about, there's some new, these are existing mines, but there's a lot of new, new mines in development that they're talking about putting it on alluvial fans or putting it near freshwater resources, putting tailings piles, where essentially it's that they extract the lithium, they have some residual, sodium chloride essentially, and they pile it. And in those cases, there's a lot of care that has to be taken so that it's not just dissolving and then flowing into freshwater resources. But yeah, it's definitely a thing we look at. Where are they doing? Where's the mine going to go? What's their plan for not salinizing fresh water? So it's something to look at for sure. Keep tabs on.
Great, thank you. All right, so for sake of time, questions from the board. So, Nusha.
Thank you guys for your presentations. I think one of my personal observation from this session is there isn't a lot of systematic analysis being done to better understand water impact of our and sort of decarbonization pathways at various scales. I think with the exception of what Brandon was touching on, maybe we are sort of like putting a lot of money, as Andres sort of touched on, in a lot of these solutions without necessarily capturing their potential unintended consequences wherever we are. I wonder if that's the right observation, or you disagree or agree. I think I'm just very curious, because what I see is very much of a, everybody is interested. They have done these studies. They're trying to understand it, but it's not they're being asked to kind of look into this before we jump into the implementation strategies.
I can start based on what I saw. Obviously, I wasn't trying hard to address the question at a global scale. I think that's really beyond my expertise. But based on what I saw, I agree with you. I think there is a lot of more work that should be done. And by listening to the presentation so far, I actually know where to look for help. So.
Yeah. So the reason I added the line from the National Climate Assessment was to point out that doing nothing is not a viable pathway, right? We have to lean into the energy transition. We have to do it in a mindful way, right? Because we know what the consequences are of conventional fossil fuel based power production. We know what the implications are for water resources. We know what they are for human well-being, and so. Leaning into the energy transition in a meaningful way, understanding, anticipating what the conversation you're having, I think is an absolutely important discussion. I think a lot of the major investments that are going in bill chips and IRA are for technology that is fairly proven. Obviously, solar, wind, these are very mature technologies for which the water implications are well known. I think obviously with batteries and with hydrogen, these are technologies that, as we heard, we need to understand some of these implications of doing this at scale. And then for more nascent technology, some of what we talked about on our planning call, right? There's I think other technologies like advanced geothermal, which the Department of Energy is really interested in for producing clean, firm power. And I think that there's water resource implications there, and that technology is much more nascent. And so I think focusing on some of those technologies that are going to be needed maybe in the coming decade to get to net zero goals, I think that's an important conversation. But in terms of the large investments that are going out right now for things like, scale up of solar, scale up of energy storage, scale up of wind, I think that is I feel confident that that's going to be a win for water systems broadly.
Well, great. So
Yeah,
with that, I think we're at time, unfortunately. Is that right, Charles?
Yeah.
So
We have
Charles is saying we need to stop, or
Is there a minute to respond to that, or is there no more
Brendan,
time?
I think we've got maybe a minute to let you close us out. And
Okay. Sure. Yeah, I'll just quickly. Yes. So those are excellent points. I think one thing I want to point out is just that, sort of we're going to need a lot more metals. And I think that realization hasn't really been fully integrated into our thinking quite yet. I think traditionally we've needed metals, but not at this scale. We need a lot more metals, and we need them pretty quickly. And the water issues to date have sort of been lumped into the carbon sort of LCA pathway. And they really require a lot more thought. It's not just water use plus whatever, or water use minus demand. It's like, it needs to be a more nuanced understanding, and I think we're working towards that. But I think it really needs to be incorporated into our our thinking. So yeah, I would just leave it with that. Thank you all.
All right. Well, thanks everyone. We're up against break, I'm being told, so we're breaking quickly, right, for just 2 to 5 minutes, and coming back right at 2:05 for the next session. Thank you, everyone.
Welcome back, everybody. I would like to invite you to take your seats so that we stay on time. My name is Pedro Alvarez. I'm a member of the Water Science and Technology Board, and I'm happy to be moderating the next panel that focuses on energy for the water sector, the other side of the coin. We have 4 renowned experts today that will give brief presentations related to what are the major knowledge gaps and research priorities and opportunities for the water sector to contribute to decarbonization and more broadly to energy transitions. And each of them is going to talk for about 8 minutes, and then we're going to have a panel for 15 minutes or whatever time allows. And our first speaker joining us remotely is Charlie Wers, who is a program manager right now at ARPA-E. He's rotating from the University of Texas in Austin, where he holds the Betty Margaret Smith Chair in Environmental Health Engineering. So Charlie, please take it.
All right, thanks, Pedro. I'll go ahead and share my screen. All right. Okay, it's pulling up. Give a sec. Okay. Hello. Everyone hear me? Yes? Okay. So as Pedro mentioned, I'm on a rotator position with ARPA-E, and one of the exciting opportunities I have is expanding the water energy funding programs at ARPA-E. Oops, there we go. And there, okay. So who's ARPA-E? We were established by the National Academies in 2007 to fund advanced energy R&D on U.S. energy challenges. Our goal is to advance high potential, high impact energy, my own quotes there, relevant technologies that are too early for private sector investment. And ARPA-E projects should have the potential to radically improve U.S. economic prosperity, national security, environmental well-being. Since 2009, we funded about 1,400 different projects across 69 different programs, and our annual funding is about $470 million. So the ARPA-E mission is to improve energy efficiency, reduce greenhouse gas emissions, reduce imports, improve energy infrastructure resilience, and then also improve radioactive waste management. The newest announcements that have come out just give you an idea of the type of funding, the amounts, and the type of projects. The first one there is $15 million for 12 projects developing high energy storage solutions to electrify domestic aircraft, railroads, and ships. The second one is $20 million for 16 projects for exploration of geologic hydrogen. And the third one there is $30 million to develop technologies to enable circular electric vehicle battery supply chain. So while they have some tangential impacts or relationships to water, they're not directly focused on water. And my goal at ARPA-E is to advance new funding programs that promote technology development at the water energy nexus. I'm currently working on developing a program for recovery of high energy value materials, and that's a focus on ammonia and critical minerals from wastewater. 2 other programs that I'm considering for the future, and I'm still looking at different possibilities, are electrification of oxidation technologies and water and wastewater treatment, and artificial intelligence for long-range water planning. And I'll talk about the first and the third one today. So when we think about high energy value materials, ammonia may not come to mind for some of you, maybe thinking about lithium or rare earth elements, but let's think about the ammonia in wastewater. If we look at the amount of ammonia in municipal and livestock wastewater, it contains about 40% of the ammonia that we produce from the Haber-Bosch process. It's an immense amount of ammonia. And globally, this ammonia represents about 4 quads per year of energy. In the US, we use about 100 quads per year. That 4 quads of energy is enough to power the entire state of Illinois, if you just look at the raw energy content. Also, when we think about ammonia, we can go back to the Haber-Bosch. We produce about 15 million metric tons annually, and about 13 of that goes onto ag fields. When we produce that grain, embedded in that is about 16 million metric tons of nitrogen. And then that grain goes to feed us, feed livestock, and also for different chemicals, such as biofuels. If we look at the wastewater that comes from all those processes, it contains about 16 million metric tons of ammonia as nitrogen. That ammonia then goes into the wastewater treatment plant where we use additional energy to convert it to nitrate. And then that water with the nitrate gets discharged. And in some cases, we treat the nitrate down to dinitrogen. If we produce the same amount of ammonia that we have in wastewater, that contributes about 1% to global CO2 emissions. More importantly, however, if we look at the wastewater process or that nitrate in the environment, we get nitrous oxide production. And those nitrous oxide emissions from ammonia in wastewater represent about 3 times the CO2 equivalent emissions for the same amount of ammonia production. So it has an immense impact both on energy and on greenhouse gases. The other critical minerals the other high value or high energy value materials we think about are critical minerals. And so we could look at some information from the IEA, for example. Here on the left, you see different types of emerging clean technologies and the different types of critical minerals that they need. And I highlighted the electric car there and also highlighted lithium. It's a major component, of course, because of the batteries. And then what you can see there on the right plot, and there's different metals there, but I'll focus again on lithium, is that production or use increase as we go from 2010 to 20, and then what we anticipate in 2040 based on 2 different scenarios, kind of projecting what we're already doing, or if we want to meet the climate, the Paris Climate Accord agreement. So you can see the growth is pretty strong. We can also look at where lithium comes from. The mining of lithium or the source or extraction of it, if we look in the leftmost plot, you can see Australia and then Chile and then China are the major sources of lithium. And then that lithium, most of it's then shipped to China, and that's where we process it, and that's in that middle plot. And so you see China is the dominant maker of lithium. You could look at other metals too and where they come from. But generally, we either import where the minerals are extracted or where they're processed. And so if we think about lithium then, in the US, on the far right there, we use about 3,000 tons of lithium each year in the US. The energy from that and the CO2 emissions related to those 3,000 tons are pretty small. It's just 10 to the minus 7 quads per year. If you compare that to ammonia I showed earlier, we were talking about 4 quads per year. And the CO2 emissions are also quite small. But what we do by replacing or having a domestic source of lithium is replacing those imports and creating a more robust supply chain. If we look at just produced water, we have about 48,000 tons of lithium available each year in what we produce now. And I'm not advocating that we continue with produced water as a source of lithium, but we also have seawater, which is a source of lithium. And so there are other avenues we can take to increase our domestic supply. So when we think about ARPA-E and our mission, we want to fund new technologies, right, that take advantage of lowering energy needs, reducing greenhouse gas emissions. And so we think about recovering these high energy value materials. And we look at the advancements that have been made in the literature and how we think that we're really at a prime point to push these technologies forward. We can look at technologies that look selective metal chelation and adsorbents or membranes that use non-precious metals to drive electrochemical reactions, or that use carefully controlled pore sizes for molecular sieving or to separate one atom or molecule from others. Another program idea that I've been looking into and thinking about is artificial intelligence-informed long-range water planning. And I'm going to use Texas as an example. If you look at the plot below, you can see from 2020 to 2070, the needs that we have for water are growing. So how do we manage that? Here's San Antonio, and I'm about out of time here, so I'll wrap this up. But in 1995, 100% of San Antonio drinking water was from the Edwards aquifers. Since then, they've gone through incredible diversification. So the question is, was this done in the most energy optimal way? And how could it be done if we approach this from a different way, thinking about energy and CO2 emissions? And so lastly, can we use AI to help transform this process? We have all these different records with water sources, water qualities, and how can we read those and digitize those so that they're in a format that everyone can access, right? Can we train AI to read those different documents and digitize that? Can we train it then to estimate the energy demands and CO2 emissions from all these different water sources and qualities? And finally, when we look at the RPE process for project development, it takes about 8 to 9 months to develop a process. It goes through lots of internal review processes and looking at relevance and impact. And one of the things we look at is, if it works, will it matter? And so we try to pick these high impact areas where we can have a difference on this energy transformation. Thanks.
Thank you, Charlie. Our next speaker is Professor Chilling Lee from Rice University. She's an expert in selective separations, desalination, and in optimizing network topology to enable distributed water reuse, which is very relevant to this conversation. Chilling.
Thank you, Pedro. If I may have my slides up. All right. Thank you. So earlier we had a session that has some wonderful data looking at globally the energy use for water. So I'm going to actually zoom in to look at the utility level. So Ashley presented these wonderful data looking at utilities in major cities in the US and how much energy they consume for both the drinking water supply as well as the wastewater. I wanted to cite her studies just to give you a reference, right? If you look at both on the drinking water side and the wastewater management side, there are many places where energy use well exceeds 1 kilowatt hour per cubic meter of either water provided or wastewater treated. And, coming back to the question about desalination, the practical minimum energy consumption for seawater desalination using reverse osmosis is about 1.1 kilowatt hour per cubic meter. So we're really not that much more energy intensive than our current water and wastewater practices. And I wanted to I wanted to point out that it's very important for us to recognize that energy consumption right now is not the primary focus of these water utilities, and they are facing multiple challenges that perhaps are more pressing to their day-to-day operation, right? Globally, that we know that the increase in water demand associated with population growth and economic development is leading us to a huge water deficit at the level of billion cubic meter. And in the United States, our major cities are also facing aging water infrastructure that's leading to astonishing loss rate of our treated water. So somewhere between 15 to 30% of the water treated is lost. That is also happening together with the secondary water contamination in our distribution network. So water utilities, in addition to energy consumption, they have to consider all of these day-to-day operational challenges. Now, so for us who are, who are interested in helping the water utilities to manage their water and wastewater better, we're trying to figure out solutions to figure out solutions and infrastructure design method that can make sure that future urban water systems can face less of these conflicts between our demand for water and our demand for energy. And one of the potential solutions is wastewater reuse, obviously incorporating alternative water resources, including wastewater and brackish groundwater and seawater, for example, together with our centralized conventional surface water sources in a distributed fit for purpose manner. And when we do that, obviously our goal is to expand our water resources so we have more sources of water to tap into, but we also need to ask us the question, what are the impacts of this practice on energy consumption, on the environmental services, on our quality of water that we provide to the customer, and what's the implication on the resiliency and reliability of our water infrastructure system. And so for this, we have to look really at the utility level. So we take the city of Houston, which has very different water challenges from cities in California here. We do have abundant surface water resources, but we have rapidly growing population. We also have very spread out city design. And so we take the city of Houston as a case study and wanted to see if we implement this sort of distributed alternative water sources across the city, how will our water infrastructure efficiency in terms of energy, water utilization, quality of the water and service to both customer and the environment changes. So here we looked at the possibility of taking wastewater and treat it to drinking water quality for direct potable applications at 9 existing wastewater treatment facilities across the city. Each of these plants can reuse up to 50% of the wastewater they receive every day. And we looked at how this might impact the overall system performance. We actually identified multiple benefits of such distributed wastewater, direct wastewater potable reuse practices. The first benefit we discovered is that this strategy reduces the overall water age in our distribution network, which is directly related to water quality. So if you look at this map here, you can see reduction in water age across the system, but especially at locations where we used to have very long water age. So the reduction can be as high as more than 20 hours of residence time in the distribution network. And so this is an indication that we can potentially improve water quality if we implement these direct potable reuse practices at these 9 locations. Across the system, the mean water age in the system was reduced by, on average, about 2 hours. A second benefit we discovered is that this distributed wastewater reuse practice can actually reduce the risk of or enhance the system resilience against disruptive events. And so here I'm showing you the potential impact of power outage at our existing surface water treatment plants. So with the existing system, you can see if we have power outage at each of the 3 large-scale surface water treatment plants, there's a large population now will be impacted by the power outage. And with that distributed DPR practice across the system, you can see we drastically reduce the number of customers that may be affected by these destructive events, which could be caused by, for example, in our region, hurricane season, we have a lot of these disruptions. A third benefit we saw is that this distributed DPR practices actually reduces the criticality of some of the major water pipes in the distribution network. And so here we rate the vulnerability of each individual pipes in the system, and you can see with the addition of the 9 water reuse sites, we kind of shift the vulnerability of these pipes from the 2 ends, the very low vulnerability and very high vulnerability, towards the center. So we have more pipes that have medium vulnerability, but significantly fewer pipes that are critically affecting the water service to the city. And the last benefit I will talk about today is the potential to reduce contamination of our drinking water supply that's happening at the source. So here we looked at if we have contamination at the 3 surface water treatment plants, how will it affect the water quality across the district, across the city? So with the 9 distributed water reuse sites, you can see that we can limit the spreading of contaminants that's coming from the main surface water supply sources and drastically reduce the average contaminant concentration throughout the system. And that's fairly intuitive because we're providing pressurized flow at this additional site to the customers. And so the spreading of the contaminant is limited to a smaller range around the source of contamination instead of more spread out across the city. Now, coming back to our question on energy, right? That's my question to begin with. What implication will this practice have on the overall energy consumption of this system? And how, us as engineers should design our system and our treatment technologies to minimize the potential energy implication. So overall, you can see here with more wastewater reuse, we have increased energy use. That's understandable. And there's also higher cost. But I also wanted to draw your attention to this wide spread of the data. So you can see there's quite a wide range of variation in terms of energy consumption for the same level of wastewater reuse. And that's indicated by the spreading in the X direction. For the same level or percentage of the water demand that's supplied by the reused wastewater, you can have vastly different energy consumption, right? So we can provide up to 16% of the city's water demand with reclaimed wastewater with zero additional energy consumption. Using existing state-of-the-art reuse technologies, you can see here, we can actually reclaim or supply up to, we can supply significant amount of wastewater to meet our demand with a net energy saving. So up to 9% of the various system configurations. So this means how many sites will provide reclaimed water and which location they will be put at. Up to 9% of these more than 500 configurations will provide a net energy saving no matter what you do. And you can also see a very large variation in terms of the cost. So this indicates that if we design the system properly, if we choose the reuse site properly across the system, we can potentially achieve a net energy saving while saving freshwater consumption and while minimizing the cost, right? So right now, if you look at our these scenarios, we have three competing objectives. We wanted to minimize freshwater withdrawal by maximizing wastewater reuse. We wanted to minimize energy consumption. We wanted to minimize financial costs. With the current technology, we're showing that there are competing interests because the water supply portfolio look quite different for each of these three different objectives. But one major reason why this seems to present a competing interest was because many of the externalities are not considered in our comparison, right? We're not looking at the benefits of reducing freshwater withdrawal, not looking at the benefit of minimizing contaminant discharge into our natural aquatic systems. And the potential public health benefits of a better quality of water in the distribution network. So the idea is that these externalities needs to be taken into consideration in future modeling efforts so that we can potentially unify these right now apparently competing objectives. And from a technology point of view, it's actually not that challenging. So this is where we are today. Only a small number of system design can lead to a net energy saving compared to all these available possibilities. But if we could reduce our energy consumption of reuse technologies down to about 1.1, again, that mark for seawater desalination, then we can make sure that anywhere you implement direct potable reuse, we can lead to a net energy saving. So I wanted to conclude by saying that there are many opportunities that we can pursue by working with the water utilities to make sure that our future water infrastructure can both meet the water quality and quantity demands at the same time considering our sustainability goals. Thank you.
Thank you, Chiling. Next, joining us remotely will be Jordan Magnin, who is the lead energy, water, and land analyst for NREL. Are you ready, Jordan?
I'm ready. Yes. Yes. Thank you very much for having me. I wish I could be there in person. I was planning on it and something came up last minute. So I apologize I'm not there, but it's been a great event so far today. Really appreciate the conversation. Appreciate you having me here. Today I'll be giving a little bit of a sneak preview of some ongoing work we're doing. I lead a multi-lab national lab consortium focused on researchers from different Department of Energy laboratories evaluating some aspects of the energy requirements and the emissions associated with our water, wastewater, and industrial systems. And what you'll be seeing today is sort of a sliver of that focused on municipal water supply. And again, it represents a little bit of a sneak preview of some ongoing work. So when we think about our energy sector or our water sector, I should say, and how much energy it will require going forward, I really appreciated what Dr. Stillwell brought up earlier. We need to think about what the energy will be used for, sort of what part of the water infrastructure it's going to be used for. What type of energy? Is it going to be electricity? Will it be gas? What are the associated greenhouse gas emissions resulting from that? What are those key drivers associating with having us see increases or decreases in that energy usage? And then I think importantly, largely for this crowd too, what are the R&D opportunities that emerge to help us avoid, mitigate, or adapt to those increases in energy and or greenhouse gases? Some of the other things that we think about that are really trends of today, and I think we're expected to continue that are going to affect our investment decisions in the water infrastructure include a changing climate, how that might affect our aging infrastructure, as well as the overuse of fresh water currently. All these things might lead to a change in our source of water. So that might be if we're moving away from fresh water to brackish groundwater or more reuse or ocean desalination. We're seeing changes in water demands, in our energy demands, in many urban and suburban areas. People have brought up contaminants of emerging concern and PFAS, where we're seeing regulatory changes that could drastically increase the types of technologies we need to deploy, as well as I think something we'll get into a little bit later this afternoon, which is thinking about environmental justice, water access, water quality throughout all parts of the United States, and what we need to do in terms of our infrastructure to really make sure we are providing sufficient water access to everyone in this country. These are sort of the existing trends that we're focusing on. And as Peter had mentioned earlier in his remarks, there's been a lot more effort focused on projecting future electricity needs and future electricity infrastructure than there has on the water infrastructure side. So with this effort, we're really starting from, really from the ground up, building off a tool called WaterTap, which was created in the National Alliance for Water Innovation, or NAWI, adapting it, linking that with some other activities we're doing to characterize operational water and wastewater treatment facilities to really get at energy and emissions at the water sourcing, water treatment, and distribution needs. We're also considering a handful of sensitivities focused on water demand, energy demand associated with water treatment technologies, as well as emissions. So as we dive into this, I'll just give you sort of our high-level outcomes right away, which are between now and 2050, we're seeing about a 13% increase, expected increase in our total water treatment energy on the national scale, but about a 68% reduction in our carbon emissions. And as we know, all water is local. Thinking about that, we can look at this regionally. We're doing this analysis at the county level, but we are, aggregating here to the state level for you to sort of see a little bit more clearly where we might see some of those trends, both in energy and then as well as in carbon emissions. And carbon emissions I think, are less interesting because we are seeing such a dramatic decrease really across each state. And we did hint at this earlier in today, but what's driving the emissions reduction is just overall decarbonization trends. And so we are seeing, despite expectations of large-scale electrification and more electricity generation, through decarbonization, we are seeing a lowering of our emission rates. And so even under, the most conservative scenarios, we're still seeing a good amount of decarbonization, which leads to a lot lower total emissions from the United States across all industries, all sectors, including the water sector. But I will say, just as in water, everything's local, we also never trust a single point estimate. And so we are looking at a large number of sensitivity analyses to try to get at where do we see uncertainties, where do we see really, these big areas where we might have more opportunities to seeing, bigger impacts where R&D can really make a big splash. So on that, we're looking at per capita changes, population growth changes, water distribution changes, alternative water resource adoption, additional water treatment needs for contaminants of emerging concern, equipment and technology efficiency, as well as overall grid decarbonization rates. Looking at these sort of as a whole, I think it's really helpful to help quantify these and really put these into perspective. So this, again, what you see highlighted is sort of our baseline cases where relatively small increase in energy needs, but a dramatic decrease in our emissions. As we think about water demand, per capita water demands, we're not seeing, even under extreme scenarios, much difference in our total energy or emissions. Somewhat similarly with our population changes, so dramatic increases or decreases in the US population, we're not seeing major impacts. Where we first start to see some real opportunities and real potential changes is with the distribution energy requirements. And so this is, we know water is heavy, it's expensive and energy intensive to transport. And so as we think about more water that needs to be transferred larger and longer distances, that potentially could lead to higher increases in our distribution energies and associated emissions. As we start thinking about more localized or decentralized solutions, however, similar to even to what Chilene was just talking about, that represents an opportunity to reduce many of those distribution energy and emission costs. They'll have other trade-offs, but I think that's one opportunity that we're seeing that could have a really big impact on the energy and emission trends. A second area where we're seeing potentially big impact is the adoption of these alternative water resources, whether it's brackish water, more municipal water reuse, ocean desalination. Adoption of these technologies, as we've heard multiple times today, can be much more energy intensive than our traditional water treatment activities. So here we could see especially many important regional trends in terms of increasing our energy usage as well as our emissions. One of the largest, I'd say, impacts, but also one of our largest areas of uncertainty is associated with treating contaminants of emerging concern. People have mentioned this and PFAS multiple times today, but this represents, depending on what types of regulatory measures are implemented, depending on what types of requirements that emerge, and what sort of technologies exist to treat these types of constituents, we could see a pretty dramatic increase in our energy requirements and our associated emissions really across every region of the United States. Equipment efficiency had a relatively minor impact, but the last big impact that we saw was in overall national grid decarbonization efforts. And so here, if we meet the nation's targets or exceed them, we potentially have large reductions in overall emissions. If we don't, we could again see sort of additional increases in our emissions associated with our water infrastructure. Putting these all together sort of in a cumulative worst case scenario chart, we could see on the energy side, worst case scenario, we could see a doubling or even a tripling of our total energy needs for our water infrastructure by 2050, or even a slight reduction. Same thing on the carbon side. We can see an overall increase from our present day emissions. In contrast with if there are, depending on how trends go, depending on how technology advances, we could actually see some reductions in emissions as well. This again represents just a sneak preview. There's a lot more that can be done, and I think the conversations we've had and some of the questions brought up earlier today have really highlighted a lot of the other new future directions much of this work could take. And I just wanted to say thank you very much for your time. I look forward to any questions you might have and addressing those in the panel discussion. So thank you very much.
Thank you very much, Jordan. Great job. And last but not least is Professor Shijong Jason Ren from Princeton University, who is an expert in water sector decarbonization, and he's going to speak to that subject today.
Thank you all. I really appreciate actually the previous panelists laid out very good groundwork. So I will expand it a little bit when we talk about water energy nexus, and I'm more like on the wastewater side, and so that's actually a great sort of understanding of the whole water cycle. I also added a book really to looking into the decarbonization pathways for the water sector. So it's a free online access book if you want to check on the details. The next slide, please. Oh, it's on me. Okay. A lot of panelists just mentioned, so the water utilization cycle accounts for about 4% globally in terms of, you can see the different sections. I won't repeat that. So basically overall, some sort of the understanding is, yes, we'll keep using energy, but because the grid is really decarbonizing, actually the emission related to the energy use in the water sector is actually dropping, right? We sort of kind of agree with that if we keep the same trend. But if you think really about the emission, when we talk about greenhouse gas emission, the water sector overall may not actually be that rosy in terms of actually the overall greenhouse gas emission. So that the figure on the right, it was done by a sort of industry consortium called Global Water in U.S. Water Alliance is basically say the water cycle in terms of transportation, treatment, discharge, even the wetland and other fugitive emission, the water sector may count up to 10% of the emission. I know the number seems to be high, so there's one actually critical research need is we really need to understand how much actually emissions the water sector contributes actually within energy and beyond energy. Actually, one question I almost wanted to ask Andreas was like when you talk about all the different industrial sectors, water has not been considered as a sector, at least from what I understand. I know DOE has been working on that. So this was done by Global Water Intelligence. So if you look at the whole water sector, we talk about the water supply side. You can see the yellow bar at the bottom is mostly exclusively about electricity related emission. We call scope 2 emission, right? But when you talk about a wastewater treatment, electricity-related emission is only about 40%. The other actually 60% really related to N2O emission, mass emission. Go back to what Charlie said. Actually, N2O emission is actually a big problem for when you treat ammonia in the wastewater. If you can recover that, not only you can recover resource, but you actually reduce that fugitive emission. And you can see that decentralized, she didn't talk about the decentralized sanitation. The main thing is really the methane leakage. And so that's sort of another fugitive emission in terms of that. So when you put it together, like in terms of really when we try to decarbonize this industry, we do look into the electricity use, primary energy use. You also need to look into, again, the fugitive emissions, and something I didn't mention was really the chemical use, construction material use, and things like that. So if you think about the infrastructure six sectors, we talk about transportation, we talk about energy sector, it's fairly defined as CO2 related emission. But when you talk about water sector, we actually cross all scopes. It's not as easy as just we decarbonize our grid, that's it. Water is much more beyond that. That's why when Nusha talk about the siloed carbon, energy, and water, we really need to get them integrated if we can. A good example where it's really UK. So their water sector put together a very aggressive actually agenda by 2030. They want to get to net zero emission. You can see, I won't repeat on the bar chart. You basically can see similar thing. They actually dissect all the different emissions related to each activities of the water utilization cycle. You do see, again, same thing for the drinking water treatment and reuse is very much exclusively about electricity, but when you talk about wastewater, about half is really about what we call scope 1 emission. And then on the little left, you see I did have a little note in there, actually from 2011, 2019, the water sector emission actually reduced by 45%, primarily due to the decarbonization of the grid, right? Grid is our great friend in terms of reducing our carbon emission as so far, right? However, there's another big research need. When you think about half of the emission related to the, say, the wastewater side, the current estimate I just showed you were mostly based on IPCC 2019 estimate, which is really limited data set and mostly based on, okay, how many people you have, what's organic loading in there, what's ammonia loading in there. There's really not really a granular understanding on the utility level. So we did a study in collaboration with my colleague, Mark Zondolo. So they did a ground up study. So we actually did about 70 wastewater utilities in terms of actually directly monitoring their methane emission in the atmosphere. And we also did a data science study, really looking into literature that covers all the actually methane emission monitoring. What we found was pretty interesting. Actually, we actually agreed on two independent studies. We agreed the actual emission of methane in the wastewater facilities is about twice as the current understanding. And that we're actually working on N2Os right now. We're working on other things as well. But it's a pretty comfort to see the actual emission related to such sector is actually at least higher than we currently know. So the big gap right now is the data. We really do not have the data in terms of on the really the ground up understanding. Right now is all top down, very rough estimates. So that's really put a water sector into an underdog situation. Like, you know, if you just trust what IPCC does, that actually may not accurately reflect the carbon footprint of our sector, and also put our sector into an underestimate that does not really catch attention on the national or state policymakers. That's what actually happening right now with all the industry decarbonization programs. The second R&D priority, I would certainly say, is like that has been done by DOE a lot. So they actually put together a very nice report to looking into the resource or energy embedded in the wastewater, organic waste, not only municipal waste, but also following the fat, oil, and grease, and food waste, and agricultural waste. So they did estimate there's actually a lot of energy embedded in the such what we call wet waste, which is a sort of a contrast with the dry biomass, like a corn stover and other biomass. So there's certainly a lot of energy embedded in there. So as Charlie mentioned, there's certainly a big sort of initiative to really think about how do we transform the waste sector into a resource sector, because there's a as Charlie said, there's a nitrogen source in there, there's a phosphate source in there, there's organic source in there. Not only you can produce energy, hydrogen, but you can produce fertilizers, can produce clean water, and also there's R&D work also actually can produce biodegradable plastic, food, actually additives, so sort of a little bit, a lot of things that you can recover. So you really can convert these waste streams into value streams. So if you really want to do a quantification, we did a work a few years back, really to say if we can actually transform the wastewater industry, which is probably one of the few, really can make it not only energy positive, as Ashley and Peter mentioned, you actually produce more energy than you consume through biogas or other process. You can also potentially make even carbon negative by embedding carbon capture process in there. So if you look at the top graph is basically the current treatment process, which use energy, emit CO2, methane, other things. If you actually electrify the first part of treatment to actually doing electrochemical carbon capture, not only you will remove organics, you can capture CO2, you produce hydrogen, you actually produce minerals. Then for the nitrogen phosphorus, I just put a microalgae process in there. Then you can capture those nutrients and then capture CO2 because they're autotrophs. Then you can produce biofuels and biochar. So after a lot of Monte Carlo simulations, we actually found the two biggest emitter countries, the US and China. You can potentially not only producing enough energy and capture enough actually CO2 to make it carbon negative, but by selling those products, you can even possibly make a revenue out of this sector. So which is very different than like traditionally, okay, we pay our sewage fee, we pay our, collection waste tip fee. So then you're done, right? Now, for the first time, if you look into the value proposition, the waste sector can even become revenue positive. So give you last slide, give you one example. So there are several big sort of utilities, or I guess the cities think about that. I don't know anybody from New York or closer to Princeton to New York. So this is Rikers Island. So it's used to be a big prison for New York City. You all know this, right? So during COVID, so they actually decommissioned, they actually in the middle of decommissioned this island, the prisons, and they tried to redevelop it. So a leading proposal is really to convert this island into the state-of-the-art water resource recovery utility facility in conjunction with renewable energy like solar panel and other things. So you would actually produce enough energy to feed back to the community, also actually recover fertilizers, clean water to be used in urban farming and other things. And even better, you actually they actually would close down 3 other treatment plants actually in Manhattan, so they would actually unlock the land so they can do actually development while using this island to serve all these other community uses. So there are a lot of potential as get into reality. Thank you.
Thank you very much. We only have about 10 minutes for questions. I was going to invite Jason and Chiling to maybe sit at the front, and of course, Charlie and Jordan are going to join us remotely. Let me begin by one question to all of you. Not all of you have to answer it, but I heard a lot about the water sector being more circular and about tapping more local and conventional sources and more distributed treatment and reuse. And if we can also commercialize some of this, is all the better. How do you guys envision that water quality and water quantity requirements will change as a result of the energy transition? And are there any blind spots or critical knowledge gaps that we need to start looking at right now?
From our study, I think we show that on the water supply side, you actually get benefits in water quantity, in water quality. One thing we did not consider and could potentially be an issue is the residual brine. If we have distributed wastewater treatment, we still have brine because you don't get 100% water recovery. I guess the question is whether you go towards zero liquid discharge or other strategies would be something we need to consider when we try to replicate this kind of model in different municipalities.
Anybody else wants to weigh in on that? Yeah. Go ahead, Charlie, and then Jason quickly.
One thing I was wondering about from the talks.
You're muted, Charlie.
Oh, am I now? It should be unmuted. Yeah, good. Okay, great. One thing that the
Still
talk.
muted. I'm sorry. I don't know if it's here, the problem, or over there.
Jordan can hear me. Let's see.
Yeah, online, we're okay.
Maybe Jason can speak while we figure out the microphone concern.
I think there's a great opportunity when you try to electrify a lot of things. Electrifying the water treatment and wastewater treatment should really give us a lot of benefits. I know now we were thinking about really in a way like traditionally we think about electricity use of our treatment is a bad thing. We try to save, we try to really doing a lot of things. But if you get affordable and green electricity in certain ways, we probably can, and it's a low grade electricity, low carbon electricity. So we probably can really transform a lot of technologies into that line that you reduce our chemical use, shrink intensification, shrink the tank. So if you look at the overall scope of the water treatment, wastewater treatment, electrification can be a very good thing to look at.
Thank you. And can we hear now in the room, Charlie? I don't know.
Let's see. Can you hear me?
Yes, thank you.
All right. One blind spot which came to mind through the talks is that as we transition to a hydrogen or an electrified economy, if we use hydrogen as a storage medium, we need water for that. And the water has to be very, very pure. And I wonder what the energy demands are on treating that water. I think by my calculations, it's about 1/20th, for example, if you look at our growth to 2050, we'll need about 1/20th the amount of water as we currently use for drinking water, but the treatment requirements on that will be much more stringent. So that could represent a large energy demand. I don't know.
Charlie, while you're there, there is a question from the audience about how can we involve regulatory agencies to streamline the risk assessment and adopt innovative water treatment technologies as they need to think out of the box and rethink treatment processes.
That was for me? Is that what you
For
said?
you and ours, maybe Jordan can also comment since we're both representing.
I'll have to speculate on my own since RPE doesn't do regulatory work. Yeah, how do we streamline that? I think there was an answer previously that I'll echo, is that I think really giving information that's plain and easy to interpret about these trade-offs in energy with water. And I think a lot of times we certainly get bogged down in the details of research and these kind of larger assessments, looking at a perspective and how we can balance that and publish these articles which show this overall balance is our best way. Thanks.
Jordan, anything to add to that, or?
I think the only thing I would add to that is, the regulatory agencies, I think, are very conservative for a good reason about, not wanting to jeopardize public health. And so the more in which we can do demonstrations or deploy many of these technologies at scale and find a way to really demonstrate that they can be safely utilized for these purposes is really going to help give everyone more confidence in adopting these more novel technologies.
Well, people think of other questions. Let me ask one to each of you. You gave us a lot of really good ideas, but if you had to pick one as a call for action, what would that be?
I think we really need to understand the carbon footprint for the water sector overall. Otherwise, we do everything based on the wrong assumption.
I'd like to say that we need to figure out a better financial model to support our water infrastructure. That seems to be the problem for a lot of the challenges we're facing.
Jordan?
I would say I think we need a much more comprehensive framework to think about and evaluate, sort of systematically evaluate our options and our decisions. So this is not just focusing on water, not just focusing on wastewater, but those together, and not just focusing on greenhouse gas emissions, not just focusing on cost, but also reliability, resilience, safety. I don't think we've yet seen sort of a comprehensive framework that allows us to evaluate the trade-offs across those different dimensions in a robust way.
I think I would echo Jordan's comment. I think when you look at the largest energy users in the water cycle, it's these large-scale water transfers. And if you think about how you optimize, or how within a city or a region or a community, how you optimize your allocation of water sourcing and treatment, I think tools to select those in the most energy efficient and lowest greenhouse gas and lowest cost way are needed.
Thanks. Last two questions from David and then Yusha.
So this morning we heard from Peter, who implored us to think a little harder about conservation, and I saw kind of an absence of that in the presentations this afternoon. So, like, for example, Chilena, you didn't talk about dramatic decreases in per capita use, or Charlie, like if water conservation goes on, we have much stronger wastewater, could be opportunities. So could you each think about, like, if we made a major investment in conservation, would it help or hurt the things that you're thinking about? And are there practical limitations to how low we can go in terms of conservation where our infrastructure doesn't perform the way we expect it to?
So that's an interesting question, and we've had a lot of discussion on this from the water infrastructure point of view, and I think really depends on the location. For place like Texas, where the population is growing, I think conservation is very important, but conservation can only get us to a certain point. But in many other places where maybe the population is more stable and potentially even shrinking, conservation may sometimes have unintended and negative impact on the water infrastructure in terms of the water quality. So I think that's a more complex issue in those places.
Can I pile on for 1 second? Mike, I had a question about the same point. Jordan, it was great to see those scenarios, but I noticed that the long-term real trend in decreasing per capita water use in the United States wasn't really reflected. You're doing some sensitivity studies, but the assumption that per capita demand is increasing is still a common assumption that's not borne out by the actual data in the United States over many decades. And the largest amount of energy use is not in the transfer sector, Charlie. It's actually in the end use sector, in people's homes. That's where far more energy is used per unit water than any other piece of all of the sectors. Thanks.
I do think conservation is critical. I would quote what Pedro said in our planning meeting. We talk about net zero energy, net zero carbon. There's going to be net zero water. There's net zero water home. I know, David, you've done a lot of work on that. So that's very important when you think about this a whole system part of understanding of the water footprint. I really like Peter's remarks. Like if you have like water saving efficient, I guess shower heads, other things. I would think, wow, if I don't need to wait that 1 minute before I get hot shower, that can save energy and water. And there's a lot of things. Actually, 80% of the energy is indeed used in water heating. And if you would reduce water use in that case, not only you would save the energy, but you would concentrate the wastewater. Actually, would allow better resource recovery. Right now, it's just too diluted, too expensive to do. Right? There's certainly mutual benefits when you think about that.
I had the same exact question. I can skip. Oh.
I
Next.
think
I'm not there. Yes.
should I,
Yes.
am I right to respond, or are we all done? Oh, okay.
Okay, no, I think that just to stay on time, we're gonna wrap it up, and let me join me in thanking all the speakers for excellent exposition. Thank you so much.
Great. Okay, so no break. Stay where you are. We're going to go to our final moderated session. Do we have our speakers online? Okay, so we've talked a lot today about the need for new policies, shifting toward decarbonization, looking at renewable energy sources. And in everybody's presentation, we talked about unintended consequences, and we really need to think about those. So now we're going to think about those. So we're going to shift to social and justice implications. There are also environmental implications as well of the energy transition's water footprint. And our panelists, Scott Tinker and Catherine Coleman Flowers, are going to help us address those issues. And Scott, you're up first. Do we have Scott? Okay. So Scott brings industry, government, academic, and non-governmental organizations together to address major societal challenges in energy, the environment, and the economy. Gosh, Scott, you must not have any time to sleep if you do all that. Scott is the Director Emeritus of the Bureau of Economic Geology and a professor who has the all-day endowed chair in the Jackson School of Geosciences at UT Austin. So Scott, please share your thoughts.
Share my screen if I could. Can you see it?
We can see it.
Great.
Yes, we're getting there.
Technology wins again. So this will be relatively brief and not told in a story form, but I just wanted to share some thoughts and data with you a little bit, kind of towards this concept of a just transition. We geologists love these ternary diagrams, but so conceptually everything has to sum to 100%. The big drivers of all of this in the world are energy security, economic security, environmental security. Those are the things that are playing. We need affordable energy, we need reliable energy, and we want our energy to be low emissions and low environmental impact. The challenge, of course, is if you have 100% of one of these, for example, low emissions, you don't get much of the others. And that's the real challenge. I just heard somebody mention trade-offs. There are trade-offs in the real world in a big way. And I've called this the radical middle. It's kind of a term I've used for many years, radically lonely. So yes, we used to cook with wood indoors many thousands of years ago, and the sun grew our hay, which powered our vehicles, and we captured the motion of wind and water. These are all the old energies, motion of bigger dams that we built, and oils for from whales that we use to light our homes. And then along came coal. Nature densified that carbon and we burn it. And, boil water, make steam, turn a generator and make light. And that changed the world. Then we found liquid hydrocarbons, more hydrogen in it, and put those in our vehicles, and then methane, of course, and finally nuclear. So these are the newer energies. And yet, and I've made films about energy poverty, we still have people cooking indoors with wood like we did thousands of years ago. Close to 3 billion. It turns out about 2.6 to 2.8 billion people, and they're dying 3 million a year from just breathing indoor smoke. So that's not just. The reason I'm showing you all of this is a pretty important concept in energy, energy density. As we went through time, we've gotten denser from dung to nuclear. The battery is a lot less dense than dung, but we see nuclear as 1 million times denser than these things. This is on a log scale. But this is specific energy or energy by unit weight. And again, that's what's happened through time. Dense energy drives our modern societies. It drives the rich world. A lot of the world isn't rich. I don't have time to show all that. But if you take nuclear out, there's a lot of advantages to going to denser. Even natural gas has less of the stuff that we put into the air that impacts our water and our land. And then other things do. You can't weigh the sun and the wind, so where do they sit? Václav Smil came up with something called surface power density, energy by area. And again, you can see a lot denser as you go from left to right. We call these things renewable. We'll talk about that in a second. And thermal, clean and dirty is what kids are learning in school. A little judgmental. Some others have come up with different terms, intermittent and reliable, or weather dependent and firm. It just depends on your perspective. Yeah, they're all got components of truth to them. I try to stick with electrons and molecules. These things on the left make electricity, and on the right are molecules, which we need to do things with. You got to have a lot of heat to make cement and steel. You can do it with electricity, but it's a big lift. Ammonia for fertilizers, for food and water consumption and plastics, etc. So we need both of these things. Again, I haven't been present all morning, but you're not going to electrify everything. We need both electricity and molecules. So here's the data through time. These are the data in exajoules. You could look at it in different ways. But these are units of energy consumed, not capacity, but actual production of coal and oil, which is dense, but it makes a lot of CO2 when you burn it. Here's natural gas and nuclear, which are also dense, and they don't make much CO or less CO2. Gas makes some, nuclear less. And then hydro, solar, wind, and everything else are not dense, but they don't make much CO2. So they're trade-offs, depending on what your objective function is, and you're looking at these things. The Great Recession of 2009, you see a drop in global energy consumption, a little dimple in of course, here's COVID. It dropped further, but we're consuming more energy than we ever have in the world today. Again, COVID did not change anything. We consume more coal and oil than everything else in the world combined, gas and everything else, by a lot still. And the reality is nothing has gone down. We haven't transitioned away from anything. So I'm leading toward the transition dialogue. We haven't been globally. Regionally and sub-regionally, yes, but not globally. And it's true, factual, solar and wind are the fastest growing sources. Here's the data. They're growing exponentially. They're starting to go linear. When you scale them and look at them in the full picture, they're there. That's the actual data. They represent about 10% of the growth in energy demand as they've been growing, of the growth, not the base. It's just this huge challenge of scale. So when we think about the climate and the air and the land and the water, the topic of this session, they're very connected. It's really one system in many ways. And I think probably we as geoscientists understand this, and earth scientists better than most. They're very connected. So the life cycle impacts of these energies that I've just gone through, from less dense on the left, bio, all the way up to nuclear, are real, particularly with water. You have to grow and process and refine and move and then convert it, carbohydrates to hydrocarbons, and then you burn for biofuels. For solar, wind, and batteries and other things, you have to mine for all the stuff, make it and deploy it and move the electrons, and then we're dumping most of it into landfills, and that's a huge water issue as well. There's water all along the way here. Cleaning those solar panels, this is from our first film, Switch, a long time ago now, in southern Spain, and coast panels wear out. They don't wear out catastrophically like this hailstorms, but they do wear out, and we dispose them. Lithium mines have a tremendous amount of water involved, especially at the surface, but even the subsurface spodumene and other things. Here's a footprint of one wind turbine, the rebar and the concrete that's going to go into that. Again, tremendous amount of heat. Burying wind turbine blades in Wyoming, and here they are piling up in good old West Texas by the thousands now as they wear out. So these are the great challenges. And then coal, oil, gas, all of it. You got to mine for the materials to drill and extract, manufacture, and then we burn it, transport it and burn it and dump into the atmosphere. So you see big coal mines that have huge impacts on the earth. Coal power plants and hydraulic fracturing uses tremendous amount of water in and produced water handling coming out. We run TexNet at the Bureau. Even waste disposal or handling of nuclear spent, let's call it fission products or fusion, spent fuels in water for cooling. So all this stuff, you're basically bringing it from the earth, it collects energy and you're dumping it into the air, back into the earth. It's not renewable. And this is something I said in a TEDx talk to 1,100 kids. That opened some eyes. There's no renewable energy. We use the term, but all of this stuff happens over and over again, and nothing is perfect. If there was, we'd do it. They all have trade-offs. So as I wrap up here, this Sankey diagram's, I think, important. Coming into the US, the width of the bar is kind of proportional to the amount. Oil is still used more than anything else coming into these four big end-use systems and into electricity, which we have to make. A lot of people don't really understand we have to make electrons. Natural gas is next, and it's very versatile, goes into all these systems. And then coal, mostly for power gen, but steel and other uses. Nuclear is next, and then biomass. Wind comes next, and then hydro, and then solar, and then geothermal. And these are the feed-ins, and out of the back side, we do useful work. We generate electricity, but only about a third of that electricity is useful to do work. And we use all the things coming in, but again, only a much smaller component actually does useful work. We waste a tremendous amount of energy. Close to 2/3 of the input comes out to do useful work. And that leaves you with this huge low-hanging fruit of efficiency. And all this affects water. And this is some work I got permission to show. I talked to Mike Weber this week. They did a long time ago, but this is kind of the energy used for water now, both direct steam injection, industrial processes, and then space and process heating kind of going down. This in 2010, we did 98,000 units, and we're about 105 now. So it's gone up a little bit. And then coming through to the direct water services and other, I don't know if you all have seen these kinds of things today, but I think they're important in all the non-water related energy, but almost half of the energy we use has water involved in it. And that provides, I think, the opportunity. So I'll wrap with this slide. Framework for a just transition. It's not binary. It's not black and white. It's not clean and dirty. It's not good and bad. It's not believer denier. I speak to all sorts of groups. I'm speaking to a university here tomorrow, here in Pennsylvania. It's very complicated. A lot of things involved in these energy, water conversations and climate. We want secure energy. It underpins the economy. The economy allows you to invest in the environment if it's healthy. There's a lot of fear that's put into this system. I'll meet a bunch of them tomorrow. It's a campus-wide talk. They're scared. The beginning of wisdom is to do away with fear. I love that quote. And we've got to get the fear out of everything, get a little bit more, maybe humility into everything, recognizing how complicated these problems are. Emerging economies, and I've visited 60 countries. There's water throughout. They don't have fresh water. They go for it from dirty rivers, et cetera, et cetera. Huge challenges here for those that are emerging. The developing, they're using coal. They're putting in shaky power lines that comes and goes. Massive dams. There I am at the Grand Ethiopian Renaissance Dam in Ethiopia. Obviously, huge systems trying to get reliable energy. And then the rich world, the developed world, hydraulic fracturing, nuclear, solar, et cetera, all using water. So when you think about these things, the odd irony of all this is we need to accelerate economic growth to have the emerging become developing, develop, so they can afford to clean up a lot of the things we talk about, from climate to water and the land and the air. So you got to grow that radical middle, advance human flourishing and improve the environment. And that's the great challenge. So I'll leave it at that.
Scott, thanks so much for your important and also sobering message. And next, we're going to turn to Catherine Coleman Flowers. I'm so honored to introduce you, Catherine. You have been an environmental and climate justice activist. And through your book, Waste, which is how I was introduced to you, you really focused attention on the problem of an inequity of the inadequate waste and water sanitation infrastructure in rural communities. And I was at EPA at the time, and you really got the attention. And while there's still a long way to go, I hope you can see that your work has energized people to focus technology, assistance, and dollars to these communities that really have inadequate sanitation, which is a disgrace in 2024. So I'm just delighted that you're with us. You founded the Center for Rural Enterprise and Environmental Justice to continue your work. And Catherine, I'm going to turn it over to you.
Yes, good afternoon, and thank you so much for that introduction. I wanted to kind of start out to explain who I am and why I do what I do so people can have a frame of reference. And I generally am known more for plain talk. I do also deal with academic institutions, and when I work with my students where I serve as at Duke, I serve as a practitioner in residence at the Nicholas School of the Environment. You know, I try to help them to learn how to communicate with people on the community level. And I think that as we talk about the energy transition and justice and what's going to happen and what is happening, I think we have to talk about history and perspective. We talk about history and perspective. I have to explain that I am from Lowndes County, Alabama. Some of you don't know where that is, but it's located between Selma and Montgomery. And I grew up in a community that was very rural. And as a result, I learned a lot about living in rural communities, but a community that was also deprived of the right to vote. And consequently, they founded a political party that allowed them to run people for office who never would have given the opportunity to run before, either as a Democrat or a Republican. So I am, you know, I come from that background, and I also have an appreciation for science. I have an appreciation for technology, but I also know that it's not fair sometimes. And the paradigms that we have developed that have created the inequities that exist throughout our society, including in places like Lowndes County, which was one of the places that had a very agrarian economy that was that was able to thrive off of slave labor. And I always remind people that I am a descendant of those people that were asked to work for free. Although there are people in government now that like to think that there were benefits that came from slavery. I think a lot of the problems that we're going to be dealing with as we talk about a just transition emanates from those paradigms that developed that we still have in place now. And a lot of the models that we have are very extractive, just like the fossil fuel industry is. It's very extractive in terms of taking information from communities and not co-designing or being involved with communities in terms of figuring out how do we get out of this mess that we've put ourselves in. So I wanted to start there to tell you who I am. And because of that, with the sanitation issue, I grew up using an outhouse and chamber pots in the house. So I know what it's like to live there and how we went from that to cesspools to septic systems that don't work. I don't want to see that in this clean energy transition. I know that we have to decarbonize our economy, and I know that we have to also make sure that people have access to clean water and sanitation. And when I talk about this and I talk about history and where we are and how do we go from where we are to where we need to be, I think we can't leave that history out. I think that we have to, I know that it was just previously mentioned how we have to get over fear, but we have to get over fear. We also have to develop trust, because oftentimes in the communities that I represent, whether they're the communities in rural areas or they just marginalized communities, period, there hasn't been trust. Not far from where I grew up is Tuskegee, and my mother was a victim of sterilization back in the 1960s. So I understand the lack of trust. Even before, you know, when we learned about what happened with men with the syphilis study, all of that has created the distrust that exists even right now. And we have to acknowledge that. And to pretend like it's not a reality is part of the problem. And how do we get to justice and how do we change this? So we first have to define what is just and for whom. Because I have been in rooms, and I've been fortunate to be in rooms that most people coming from where I come from don't get a chance to be in. But in those communities, sometimes when they talk about trade-offs, they're not talking about trade-offs for themselves. They're talking about trade-offs for those people that live in marginalized communities. And I serve on the White House Environmental Justice Advisory Council, and I serve there with people that live in Louisiana that are very, very concerned about the projects that are being supported, but they're concerned because there hasn't been that trust, and that fear is not something that they are imagining. I got the opportunity to go through Cancer Alley with General Russell Honore. If you don't know General Russell Honore, look him up. But he rebuilt New Orleans after Katrina because he was in the military at the time, and he was sent there to bring stability. And as from that time, he has now become an environmental activist. And he actually took me there and he introduced me to people in Cancer Alley. And one of the persons just was recognized at the time 100 most influential people in the world, Sharon Levine. And Sharon lives next to a plant that is a polluting plant. Almost everybody in her family has cancer. She's even battled with cancer herself. And we wonder why people don't trust these new technologies and whether or not we're going to do the right thing, because we have not been doing the right thing. And we need to change that. And we need more people to be outspoken about that. Because if we don't, we're going to all burn together. Because at the end of the day, the people that I know are protesting these new technologies. They're not open to them because of the fears that they have, because of our history and what has happened before. The other question we have to talk about, if we talk about this energy transition and water in particular, is who has access. When I think about that, I think about a meeting that I went to at the Aspen Institute several years ago, when the people that were the big growers in California didn't even want any controls over groundwater, so they could they could actually drain other people's wells. They wanted the controls to be in their hands. Or we can talk about the people in Detroit who have been getting, because of the failed infrastructure there, they were putting water mortgages on their homes and taking their homes for a water bill, but they weren't doing the same thing for the businesses that had big water bills. Likewise, when we talk about who is harmed, and we talked about how do we get to justice, you know, just before getting on this Zoom, I just read we're in Flint. They're still dealing with lead in the water. There's still some pipes that have not been replaced all these years. So in order for us to get to where we need to go, we can't forget about the things that we still haven't addressed to get to where we need to go at this particular point in time. And I'm very concerned about what some of these projects may do to water, who is going to have access. And this is going to lead to more privatization, more commodification of water, and who gets left out. And the people that we're seeing getting left out are in these marginalized communities. But lately, I had the opportunity a couple of weeks ago to go to Albany, New York, where I was recognized on the Senate side and in the General Assembly for my work. But what was so interesting to me was all the people that came to me from rural communities and urban communities talking about the problems they're having with water infrastructure. I even spoke with an assemblywoman who represents part of Brooklyn, who showed me videotapes of the drainage system that's so messed up where her constituents live. They have a garage that they have to enter from the back, but they can't park in the garage because it's full of sewage. And they were showing me the rats that were in the video that were back there. And whenever they went to try to get help, they were told that it was the responsibility of the homeowners to fix it, although this is a problem that's caused by a failed design and infrastructure. So one of the things that we're finding, and I'm talking to young people about every day, is that we need to design, first of all, we need to co-design systems with people from the community. One of the things that's left from a lot of these equations is authentic community engagement. And oftentimes the communities are on the butt end of when stuff goes wrong, but they're not included to figure out what the solution should be at the very beginning. As we talk about these different technologies and how we're going to decarbonize our economy and how we're going to decarbonize our energy systems, we have to figure out how we not do additional harm. How do we not perpetuate what we've already put in place? And I often say, as we talk about justice, coming from where I come from, I know that a lot of our economy is based on a plantation economy where the labor doesn't get paid and is free. You know, I live in a state right now that's fighting unions left and right because they want people to still make $7.20 an hour, which is the basic minimum wage here, but that is not enough for a family to support itself. I come from a state that if I had the ectopic pregnancy I had several years ago and I had it today, I probably wouldn't be here to talk to you because I would die because the doctors wouldn't be able to talk to me and make good decisions about the health outcomes that I will encounter. So those are kinds of, it's through the background of all of this that young people are afraid. They're afraid of the technologies. They don't see justice. They don't see things being deployed the way they should. They don't see people speaking up and saying that this is wrong because folk are more concerned about continuing to get the funding that they get at the institutions to do the studies than to say this is wrong. We need to do this a different way. So I think that the way we get to justice is one, we have to make sure that we have to make sure that there is authentic community engagement. Authentic community engagement means wherever these projects are, it shouldn't just be a community. The bare minimum, the minimum standard shouldn't be the community development plan that the Department of Energy is requiring. It should be actually spending time in the community. It shouldn't be helicoptering in long enough to get the money, to get the grant, or to get the contract, doing a design and leading, not to seeing what harms are there. We need to also make sure that there are entrepreneurial opportunities in the communities where we're doing these projects. That is not just people coming from the outside, these big universities, the big contracting engineering firms coming in, getting all the contract and taking the money with them. That's what keeps the communities poor. We have to find out, how do we train people to maintain this? I live in probably, I think, one of the most educated parts of Alabama. I live near Huntsville. We have more scientists and engineers here per square mile than probably anywhere else in the country. In my backyard is the Marshall Space Flight Center. Most of my neighbors are working over at NASA. If they're not working at NASA, they're working for government contractors, defense contractors. So there's a big emphasis here on STEM. But I cannot find a person who can put solar panels on my house and maintain them because people are not being trained to do it. They're not putting in place, if I wanted to move from a car that has an internal combustible engine to a car where I can use clean energy or use electricity, where am I going to charge it? Because there are no charging stations here. So I think that as we develop these plans and we look at how we move to where we need to go to decarbonize our economy, we got to make sure that justice is at the bedrock of all of this. Because if it's not at the bedrock of all of this, we're going to do what we've always done. The people that can afford it will get it. The people that can't afford it will be left behind. And with what is happening now with climate change, we also work with my organization, the Center for Rural Enterprise and Environmental Justice. We work at the intersection of health and climate. One of the reasons that I'm probably being recognized for my work is because I did a study with Dr. Peter Hotez at Baylor School of National Tropical Medicine, where when I was talking about sanitation and lack of sanitation, first of all, people would not even admit that it exists in the United States of America. That was a third world issue. And the second thing is that we did not acknowledge that hookworm and other parasites that we associated with underdeveloped countries were here in the United States. But when I went to Dr. Hotez, he listened to me. And he was able to send his parasitologists, and we worked together with the local community to collect those samples. And we found out and found evidence using the scientific method and data and technology to realize that this is indeed a problem. And that's what has focused a lot of attention on solving these issues. But it was because of our working together with the academic community. They listened to us, and they didn't just helicopter in. They listened to us, even when it came to collecting the samples, when they wouldn't give it to the scientists that came from Baylor. But he listened to us, and we said, you stay in the hotel and we go get the samples so that we can make sure that we do this study. That's how we're going to have to do as we talk about this energy transition and how we deal with water, because I'm very concerned that the water that has already been poisoned and could be poisoned, and the limited access that will happen is not going to happen in the more affluent communities. It's going to happen in the marginalized communities. And we have to ensure that this does not happen again. And the speaker before me mentioned Texas. I was just in Texas a few weeks ago. I actually went to the Colonias. And what I saw there is an atrocity. That as we talk about all these things and what's going to happen in terms of the new clean energy economy, we need to make sure that people get basic things. I saw people there living in campers that they had added on to make a home. Some people didn't have electricity. And these are not people that just came over the southern border. Some of these people have been here longer than Texas was a state. And we have to do better. So if you don't remember anything else that I've said so far, we got to ensure justice. Justice means doing the right thing. It's just that simple. And the trade-offs shouldn't be the trade-offs for the people that have had the trade-offs all the time. Some of these people are still burning wood. And the previous speaker mentioned that. They're still burning wood. There are people that don't have anything at all. They're trying to make it the best way they can. And I think that we're at a pivotal point now where we can not only bring about justice, especially environmental justice. It's a time for us to transition away from plantation thoughts, from plantation paradigms and business paradigms that only support profit and don't support people, because that is what has gotten us in the situation that we're in right now. I thank you for the opportunity to have this, to share my thoughts. I'm open to questions, and I think that we have to think in terms of no matter what kind of political the political scene that we're dealing with right now that is very antagonistic and very negative, we have to think about how do we change things in such a way that we can get to justice, we can get to clean energy, and we can save the planet for 7 generations to come. Thank you very much.
Thank you so much, Catherine. Sobering but inspiring at the same time. At least that's how my feeling about your remarks. So we're going to turn to some Q&A. I guess we have 10 minutes about. So I'm going to start off with a few questions. And if you want to ask questions through Slido or put your tents up in the room, I will call on you. We have 15 minutes. Okay, great. So I want to sort of reflect on everything that's been said and have each of you talk a little bit about how do we do that balance between local environmental and human impacts and the global footprint, sort of the idea of who's impacted versus who benefits that you both alluded to, with some of us living in ultimate technology and others without sanitation or electricity to cook. So Scott, I'm going to turn to you first to offer us your thoughts on how do we do it.
Well, you have to recognize, I think, that disparity exists. And when you look at people living in energy poverty, it's not just those with nothing, although there are about 1 billion people that have nothing. And that's what our second film was about, visiting those communities. But there's another 4 billion or so, Ellen, that are living in some level of energy poverty. That means the lights come and go, the fuels aren't always there. It's a existence that we would not put up with in the rich world. Okay, we demand it 24/7, 365, affordable and reliable. So with that challenge, you have to look on the energy side, and that involves water, of course, is what is affordable and reliable to people. And that's going to vary geographically by region, and it even varies within our own country. The Colonias, Catherine, you mentioned, is a huge example of things that are completely unjust and no need to be. Okay, but there it sits. And so I think the challenge becomes not implementing or imposing a certain set of prescribed solutions on these things. Asia needs coal. They're using coal. It's affordable and reliable to them. They're making all of our stuff with cheap electricity and sending it over to us on barges and things. We expect that cheap. So taking away coal from Asia right now would have a massive global impact. Instead, we have to help them think through how to transition more quickly to other options like we've done, or working with carbon capture and other technologies, some combination of things. So a little less prescribed on the front end and a bit broader look at the outcomes on the back end. What are the actual outcomes that we're succeeding in? I think we're working on a study right now, and this will be my last point, comparing some electricity options, and we're doing a really rigorous life cycle analysis of these things. It's really hard, by the way, because you got to go from grassroots to basement, if you will, all along the way. But an LCA of water and energy is very valuable. What are the real surprising places that impacts to the environment happen, and who really is paying for those, both in terms of the financial, but more importantly in their communities, by those being imposed on them in a variety of ways. Water being used and dumped, power plants, electric plants of various kinds, solar and wind farms being put into places that are can't fight that, you know. So this is really a look at optionality. I'll leave us with that word. A portfolio of options is very powerful, and it makes a lot of sense in energy and water, and we can't prescribe the portfolio, if you will, a priori. It's going to vary very much geopolitically.
Catherine, your thoughts?
Well, my thoughts are, first of all, we have to have that authentic community engagement.
Mm-hmm.
That's how we build trust. And that's also how we help to build acceptance in the communities as well, is that they have to be engaged from inception to implementation. And that's a large part of the problem, because people resist things that are being forced on them, as opposed to them being a part of it. And I think we also have to talk about that just transition. What does that look like? You know, I have friends and family that work in the oil fields. You know, I'm an environmentalist, but I know that they have to have a way to support their families. And we're not going to convince people that just because the earth is burning, that they shouldn't work there. They want to be able to support their families. Just like the people that I know, like my uncle who died from black lung disease because he went into a coal mine. He went in that coal mine, not because it was the best job, but the best job he could get. It was a high paying job. And it also provided him with an opportunity to support his family and put his kids through college. We have to provide those kind of jobs and trainings and options. And people have to see that. They don't see it yet. And until we do that, we're going to have resistance. And those are going to be the biggest challenges that we're going to have to overcome, is how do we get to acceptance? And we don't get to acceptance without having that just transition, and also making sure that communities are engaged now, not once the plans are made and put in place, and then trying to get them to accept it. It's too late at that point.
Yes, totally agree. That
Catherine, there's a real good
obviously-
example of that. When Texas put in all the wind through time, we have 5 major power lines, 345 kilovolt power lines, and you literally had to go community, ranch by ranch, farm by farm, community by community to get approval for that. That's very hard work. And one of them wasn't built as a result of that on the ground work. But you're exactly right. Without community buy-in, none of this happens.
Okay, I'm going to turn to some questions. Thank you so much. Crystal.
Hi, Crystal Tully Cordova, Water Science and Technology Board Member, Principal Hydrologist with the Navajo Nation.
Thank you for your presentations here today. You know, one of the things that I'm curious about is, you know, those people who continue to be impacted with regards to access. So, you know, we're talking about water and energy from a standpoint that everyone has water and energy. When we talk about the Navajo Nation, you know, a third of the population doesn't have water and an equal amount doesn't have energy. And we think about energy from the perspective of, you know, coal burning power plants. In the Four Corners region, you know, there were several coal burning power plants, and those have been decommissioned. But even before they were decommissioned, the majority of that power was going to LA, going to Phoenix, going to Las Vegas. And so when we think about you know, something that resonated with me was what you said, Catherine, you know, the people who continue to get taken advantage of may continue to see the impacts. Whereas, you know, if you're not at that table creating some of these solutions, then the perspective is that there's no impact. And, you know, I guess one of the things that I'm curious about and how to be able to address this issue of those getting hit, continue to get hit, either with extraction of resources or inaccessibility to the basic necessities that have built this country, meaning water and energy infrastructure. I guess, what are ways to be able to describe, you know, for those marginalized communities, those rural communities that continue to get hard, and especially as we talk about decarbonization, how can we be able to, I mean, so we talked about lithium, we talked about hydrogen, but when we think about some of those communities that are concerned about that, for example, in the Salton Sea area, the Khitan and the Kokopah are really concerned about, you know, lithium and that industry booming, and other tribes like the Navajo Nation with a hydrogen pipeline that would be going from the Four Corners region where Shiprock, New Mexico is, all the way across to north of Flagstaff, Arizona. People are really concerned with that. So then even though when we're thinking about these decarbonization projects, there's really much more concern, not only about access, but also what are those environmental impacts?
So, Catherine, I'm going to turn to you first.
Yes, I think, yeah, I was just on a panel this weekend. South Carolina Education Television did this panel, and I was on there with a number of people. The co-vice chair of the White House Environmental Justice Advisory Council is from New Mexico. We had people there that were from Arizona and other places, and that's one of the things that when we were looking at environmental justice from Clinton to Biden. And that came up over and over and over again, and people are against what they call false solutions. And they're very concerned about the solutions that are being put in place and the impact that it's going to continue to have on them. And it goes back to what I said earlier. We have to make sure that we deal with those things that we have not dealt with. The colonialists was one example, Navajo Nation is another. But there are numerous examples around the country where we have not dealt with making sure that people got equal access to infrastructure like water and sanitation, as well as electrification. So I think, again, that part of the way to break that is to break in is to be vocal. Community engagement, push for community engagement, going to the meetings. What we've done, when I first started doing this work in 2002, they weren't even acknowledging there was a wastewater problem in the United States. But I kept telling the story. And the first people that I told the story to, they were US publications that didn't even want to cover it. I had to talk to the Guardian because they were interested in telling the story. That's why when our study was, after our study was peer reviewed and we released it publicly, we didn't release it to a US paper because they had denied that this was a problem. We had to do it with the Guardian. So storytelling, I think, is very, very important to make sure that local people get a chance to elevate their voices, to talk about what they're currently dealing with. I mean, that way you keep it impossible for people to ignore it. Also, with my service on the White House Environmental Justice Advisory Council, there's a period when we have those meetings for comments from people from the community. Attend those meetings because the people from all the federal agencies are listening. And please have people to state what they're dealing with, because I know that people on the WEJAC are listening and people in the White House are listening too. The other thing that I suggest you do as well, in terms of that, is whenever they're talking about these projects, there is a comment period. people don't know about it in a lot of cases, but if you sign up for some of these at least the WeJack, and go to their website from time to time, these things are listed so people can speak up and speak out about the concerns that they have, and also force these entities to do the community engagement that the government is requiring, that the federal government is required that they do before these projects can be implemented. So those are my suggestions at this particular time.
Those are great suggestions. And yet you have to be there to be heard.
Yes.
And you have to force the government to follow their own rules, because sometimes those comment periods are abbreviated. We all know that. So excellent. I'm gonna we have a couple more questions in the room, so I'm gonna turn to Andres. You had a question?
Oh, you can use that.
You can just use your speaker right there.
Okay. Okay. Catherine, I want to thank you for your remarks. This is Andres Clarence from the White House. The goals of environmental justice, labor, and climate are sort of all equally important in this administration, and it's been really exciting to sort of see that in practice. And to some of your points around sort of mature technologies like solar panels and EV chargers, you know, I don't know if any of you all saw the announcements around the green bank investments and the efforts within the administration to make financing available for some of that infrastructure to be built out. My question for you is, do you have any examples of community engaged activities you've been engaged in where the technology is a little further afield? Because a lot of what we're talking about today doesn't exist in the same way that solar panels do. We're talking about like green hydrogen, we're talking about carbon capture, we're talking about carbon dioxide removal. I mean, these are all technologies that are largely notional. And so going into communities and asking questions about these things and how they will impact people is still, it can be challenging because it is still it's still an idea. I don't know if you have examples from your work of places where emerging technologies have been considered by communities that you've worked with, and that has helped refine the process of developing those technologies.
Well, I think that one of the examples that I can point to is that we're actually working with the town of Whitehall, which is located in Lowndes County along the Selma to Montgomery March Trail. Not so much about these clean energy technologies per se, but even just to deal with something as basic as sanitation. The administration actually sent Mitch Landrieu a couple of years ago to reach out to me and Michael Regan, and also the U.S. Agriculture Commission. Agriculture Secretary came to Lowndes County to announce the first ever closing the wastewater access gap initiative. And what was found in that whole process is that, and I think Scott mentioned it earlier, that the solution was different in different communities. And we also have to think about, when we talk about the technology, it's going to be different in different communities. There's going to be different ways, different types of acceptance, and the conversation that you have with the community has got to be different. The conversation that you will have in Huntsville, Alabama, is going to be different than the conversation you're going to have in the Colonias, different than the conversation you're going to have in Lowndes County, Alabama, because you're talking to scientists and engineers here. So they're kind of, the questions they're going to have and their response is going to be very, very different. And they may not have the fear, whereas in the communities that have been marginalized for so long, they are going to have the fear, and that has to be addressed. In terms of examples that I've seen that works, I saw a community in Texas. Texas, I think Texas has a whole lot of renewable energy projects that we don't know about. They're actually doing more in Texas than they're doing in a whole lot of other states. And I saw a project in Georgetown, Texas, where they're actually developing, they're partnering with a company called Icon that is in Austin. Icon is using 3D technologies to print homes. And they also have a contract to build a lunar habitat on the moon. And we were connected to them through the people here at the Marshall Space Flight Center. But they're using that, and they're building those homes using renewable energy technology. And I think they were on 60 Minutes a few months ago. But I think here's an example of how it works because there's a demand in that community for those type of homes. Now, it may be a different kind of demand somewhere else, but they also built, not only did they build those homes at a market rate, there's another part of Austin where they built homes for people that are homeless, doing the same thing and using renewable energy technologies there. And I think that there's something to be learned from that process and how they were able to do that. So those, you know, unfortunately, I haven't seen a whole lot of other examples yet because a lot of this is
Those are
new.
great points.
Yeah.
Scott, did you want to add to that? And then we have one last question.
Sure. I think the challenge here is with low density forms of energy, the local impacts are much, much higher. They just are. I'm a geologist. I don't mind mining, but mining is not green, and it never will be. So the land impacts from mining are tremendous, and the water impacts from that. And as you start to build solar panels and wind turbines and batteries, and we have the leading CCS group in the nation. We've been at it 25 years, have a hydrogen consortium. We're looking at these things, but the infrastructure that has to be built to capture the materials, the metals, and make all this stuff, including batteries, and then move it to where it's going to be used. And then the landfill disposal that happens after that, we don't recycle and reuse. We talk a lot about it, but it's more expensive. So we don't 5%. So that's, I think we have to be more honest. I think, including in the White House, you need to be more honest about the impacts of energy, and there's no green or clean energy. The solar and wind and batteries have their challenges, coal has its challenges, oil and gas has, and we have to be honest about not just who produces it, but who uses it. Where is all the electricity being used today? That's the demand end. That's mostly tech, the things we're doing right now, massive amount of electricity demand. Most people don't have access to that. So the global challenges of climate and some ocean things are one challenge. But the Salton Sea you mentioned, the question mentioned earlier, yes, they don't want that mining done for lithium in their community. Yet Gavin Newsom is going to mandate EVs. Can you see the irony? Maine, they don't want to mine the spodumene, the lithium in Maine. That's the other end of the rich scale. Yet they're going to mandate EVs. Can you see the irony? So we have to start being a little more humble and quit competing these things against one another. That is a failing strategy. We are pitting ourselves against ourselves when in fact all these things are needed in different ways. And that's the great challenge, is to bring get rid of this false narrative of good and bad and start investing in things that matter for each of these communities, live with the community, with the earth. A lot of these jobs would be good for people if they were done well. Lithium mining in and of itself is not bad if it's done well, and it's good jobs. Manufacturing of various things. So I'm 65 years old almost. Have been doing this a long time. Okay. And it's frustrating to see the dialogue going apart now more than coming together. It will not solve things.
You both bring up great points, and I think it all relates to, again, involving people in the beginning so trust is established and understanding, and how something can be done in an environmentally and socially sound way and benefit everyone, if that's possible. Okay, I'm going to turn to Camille, who is one of our board members, for the last question. She is online.
Thank you. Can you hear me?
Yes.
Excellent. Thank you both so much for your comments. This has been fantastic. One of the things that really struck me, Catherine, was what you were saying about the plantation paradigm and how that continues to inform the ways that we're set up. And I wondered if you could talk a little bit about, sorry, I'm trying to figure out how to make this short, but one of the things that I find perplexing is that a lot of the work in the energy sector is repeating the fossil fuel model, but just with like clean inputs. And one of the things that you've done in your work in Lowndes County that's been so inspirational is you've really done a lot of interesting technology jumping. So you've showed that we don't have to use old models that don't work in all communities to make improvements. And I was wondering if you could talk a little bit about whether you see there being some applicability in the energy sector. Are there things we should be doing differently or thinking differently when we're in Navajo Nation, when we're in rural areas or in Lowndes County, that could also inform how we're doing things in cities possibly, but we're too stuck in the old model to see beyond kind of the way we've done it before.
Well, I think first of all, thank you for that question. I think first of all, one of the problems is the way these paradigms are set up. It's set up for profit only, and not for the impact on people. I've heard too many times, even when it came to sanitation, we can't use this type of technology because it's too expensive. But what do? We sacrifice people. We sacrifice health. We sacrifice the public health when we do that. And I think that's one of the problems and one of the things that we need to eliminate. I think we also, and I keep going back to community engagement, that it's going to be different in different places. And we have to get the local people involved and engaged where they understand it. Because the worst thing we can see, we have whole campaigns, national campaigns in this country run on untruths. You know, even if we talked about, I think Scott just mentioned some things about how things are being pitted against each other. Well, one reason why it's happening because the fossil fuel industry has put a lot of money into marketing and pitting these things against each other. So we also have to, but we have to make sure that there's authentic community engagement. We have to make sure that these technologies, that we tell the truth about what the pros and cons are. I think we have to also make sure that we have some good pilot programs that people can turn to see how it works when we do it right. They need to see that because we have so many examples of what happened when we do it wrong. And what's even more importantly, I guess for me, I just read where the UN just said, and I think he was being dramatic when he said this, but not so, because I'm seeing how the weather is changing here, that we have 2 years to get this right. So we need to come up with some processes that work, and we need to make sure that there's the involvement and the buy-in of the community, and that's only going to happen when we go to them and get their input and have representatives seated at the table.
Thank you very much. And with that, I'm going to close out the sessions. First of all, let's give a final round of applause for all the speakers and conversations. And I'm going to turn it over to Nusha to close us out.
Thank you. Thank you, Ellen, and thanks, everyone. This was a very informative day. I personally really appreciate everybody's comments and remarks and all the discussions we have had. I have a few points I wanted to make, which is sort of drawn from all the comments we've heard today. I think we talked about rethinking our institutional setup and how we can bring water, energy, and carbon together to think a little bit more about synergies and opportunity areas rather than constantly moving on our own silos and hoping that the other lane is going to do the right thing or will have enough resources for us or bring what we need to the table. Another piece is there's a dire need of system level thinking and resource management to basically be able to achieve both resilience and sustainability, both for water and energy in the future. And then I sort of came out of this thinking we really do not have a lot of understanding of water implications of our decarbonization pathways. And obviously, a lot of this does depend on mining in different ways. And, I appreciated Charles' comment about how we can, look at brine as a resource, but do we really have a market to spend that much money to mine the brine for lithium when somebody else across the world can generate it for a fraction of the money that we can do it? How are we going to overcome that, economic reality? So it kind of makes me wonder, do we really have a very good understanding of this? And is it like out of sight, out of mind kind of a strategy here, right? They're mining the coal, mining the, all the metals and resources that we need, and we use them here, so it looks much cleaner. So what's the line here and how we can minimize those? I also sort of came out of this thinking in many of these cases, we are not really thinking how climate change is going to impact the underlying assumption of our system level analysis. we are sort of assuming certain things will stay the same while we are transitioning, and that's not really true. You know, from sea level rise to droughts to storms, like we are really dealing with fast approaching or like current drama around disasters that we're dealing with, from wildfires and sea level rise and drought. So the question is, how are all those impacts are going to impact some of the systems that we have, and how are they going to function in the long run? And I don't think a lot of these analysis we are doing is incorporating those changes. We also talked about contaminant of emerging concerns. It's not just PFAS. We are producing left and right man-made chemicals that are being used for various reasons. And a lot of those are impacting our water resources. And the question is, who's going to regulate them? How are we going to deal with the pollution that's being impacted? And to be honest with you, we are right now dealing with unintended consequences of the decisions we made 50 years ago on putting our industrial waste in our groundwater basins, because we never thought we need that groundwater basin. So now that we need it, we need to use a lot of resources to clean it up. I think from the last panel, I came thinking, we really do need to better understand the trade-off. We do need, I appreciate Catherine's comment on authentic community engagement. It takes time. It requires value systems. That it's not something you can do just because we are having roundtables or comment sessions. Doesn't mean that we are really getting to the heart of community needs and concerns. I mean, think about people who can attend these events or provide comments. Half of them don't have time to really engage in a bureaucratic process that we have. So how do you create a sort of an easier level of engagement for people to bring up their comments and concerns to the table? I think local workforce development is very important. We heard the fact that people make decisions based on having, being able to provide for their families. So do we have alternatives for the existing systems that we have, and how we can create one? And I would just lastly say, storytelling is a super important issue. And we really do need to think about that. And I just close with by saying, there are so many synergies that we can take advantage of. I appreciated Scott's comment on how much the energy that we generate is wasted. We also waste a lot of water. We also waste a lot of other resources. So the question is, what are the efficiencies that we can take advantage of, and synergies that we can take advantage of to minimize the impacts, reduce our demand on our natural resources, and be able to move forward in a more sustainable way? With that, thank you, everyone. And David, do you want to close?
Just say that thanks everyone for joining us today. Thank you, Nusha and the steering committee, for organizing a wonderful day. We're going to end the Zoom panel now, but those of you who are here are welcome to stick around for some informal conversation. No need to run away. They don't lock up the building. You won't have to clean up the cups and the lunch stuff. Okay, thank you very much.